I hope you signed the attendance sheet. Please do make sure to mark your attendance. For online, we also have been tracking the Zoom log. So at the end, we are monitoring complete attendance. On complete attendance, we'll be issuing the certificates at the end of the course. So starting off with our first lecture for today, I'd like to invite Professor Dr. Farhan Saab to introduce our speaker for the day.
Assalamu alaikum. In our first session, we have Dr. Abdul Razak Saab, and he's going to present his work on mathematical foundation of quantum computing. He is serving as senior faculty member at NUST. Dr. Razak completed his MSc in mathematics at Government College University. And then he did his MS and PhD in cybersecurity at NUST. Later did his postdoc from UK. In last 6 years, he's working in quantum technologies. He has introduced quantum cryptograph, quantum crypto, post-quantum cryptography, quantum machine learning at NUST, and he's member of various technical committees on quantum workforce at Ministry of Defense. He contributed in national quantum strategy development as well. And he is having a distinction that he has introduced first MS Quantum Information Science program at NUST as well. So here I invite Dr. Abdul Razak Saab, please.
Bismillahirrahmanirrahim. Assalamu alaikum to everyone. Okay, thank you, sir, for nice words. So, this is my topic, the Hilbert space to qubit. So, this is the topic. So, this will be. So, first of all, I will highlight the strategic importance of this domain. Then the at NUST level, what the initiative they have taken. Then the motivations. These are few slides that is a part of my every presentation. Correct? This is a motivation, at least for me. Then we will go for quantum math in detail. Okay, if we see the historical warfares, the first major damage to Japan was due to the operation of Midway because of information theory. Cryptography, Enigma cipher was started decrypted by the Allied forces. This was the major damage after Pearl Harbor to the Japan. And complete defeat was after the throwing of the atomic bomb because of this theory, atomic theory. No current era, this information, quantum information science, this theory is now merged as a atomic bomb of a new information era. So this is the actual importance. So this lethal technology is we are using in the warfare. So in quantum warfare, this was the news. The Chinese say this is a fake news, but they are giving some traction. So the Iranian soldier, the American soldier was rescued by the quantum magnetometry. So by detecting the heartbeat of the soldier. But it is used in all the domain of the warfare. We are actually working in this area, communication, for making our communication more secure in quantum era. So if you see the historically breakthrough in the technology, so current era is that of quantum technology. So at NUST level, we have an initiative Quantum Information Science Group. There are the global participant in that. We have workshops on the application in defense technology, introduce the courses quantum cryptography, quantum computations, post-quantum cryptography courses for UG or PG. Then we have a project on post-quantum cryptography, quantum cryptography. These two projects we have completed successfully. So quantum technology lab, we have three labs: applied physics, optics lab, and at NSTP, that is 5G innovation lab, we are working on in the area of post-quantum cryptography. So we have submitted some project in a PAK KSA Turkey collaboration under this is taken care by the defense. And quantum machine learning for UG, we have introduced quantum programming, quantum sensors. Now we are starting in the fall 2016, quantum information science. This is our ad. This date will be extended. This is the first program in Pakistan, quantum information science. So we will cover the latest quantum cryptography, post-quantum, quantum machine learning, such like topic that is the need of the hour. So we have had this workshop on quantum warfare, quantum programming, quantum post-quantum cryptography, quantum AI, and we are also exploring one of my PhD student is doing, that is the dark web, how we can have a layer of dark web for communication behind the enemy lines. Because when we are communicate with the head behind the enemy line, normal encryption, it can be detected because encrypted packet can be detected. But when we have a layer of dark web technologies, then it will be look like a gaming packet. So it will be hard to detect. So this is the on cybersecurity workshop. This is actually start. So why we are here? This is actually starting with the motivations that talks. What is the purpose of here? So every organization having the mission, vision, objectives. Before that, it has a global feasibility analysis. So these are the four parameters that every sector, if you want to start your own life, you have to see these factors. But in our universe, so overall generalized form, because every company mission objectives that will be addressed to this specific company, and they are addressing a very niche market, all right, limited, they're addressing the need of a very limited people. But generalized form we want to see as a Muslim, globally we have to believe that this is the order of Allah, even it is implemented in our body also. So, innal hukma illa lillah. So, vision, what should be? Vision should be that whatever we are, doctor, engineer, student, whatever your role may be, but the end of this life, when your God see you, they say, okay, well done. You have done very well in the world. So, this is the Fatila, Rabbiki Radiyatan Mardiya, Wasflifi, Ibadi Wasflifi Jannat. So, this is a big vision. So to achieve this one, we have a big mission also. That is very easy for us. That is in follow this Sunnah of Holy Prophet Sallallahu Alaihi Wasallam. We can easily achieve this vision. How we can make objective? One key element, remember, that is Khairun Nas equal Nas. Whether you are a doctor, engineer, whatever. So one element, if you add in your objective, you have to think about others. So you will achieve your mission, then vision, and you will be successful. Not only in this life, but also in the life after. So this is a revelation book, believe me, wonderful. All right. This is not the normal one. This is the actually a book that can give the dignity and honor to the nations. It has a big claim that is, there is no doubt in it. And the Viana Gulish and no, everything is present in that. So this is a big claim. So I just want to refer to the scientific theories. In the past 1500 years, the science have deceived people that the Earth is stationary. Then next 500 years, okay, Sun is stationary. But in the Holy Quran, 1400 that it is mentioned that everything is removed in a given direction. It provides a research methodology that is more comprehensive any research methodology given in the our books. We have, if you see that there are a lot of Muslims, if you Google who is the father of quantum technology or optics, you will see this name, that Ibn Hisham. So you see your forefather that have scientific discoveries when his whole Europe was in dark ages. So 2022 Nobel Prize, this is a wonderful revolutionary Nobel Prize on the basis of entanglement. On the entanglement, that two particles are at distant place, but their communication will be instantaneously without delay of time, even their distance is galaxies away. So something feel that there is a something is moving with the velocity of light, more than velocity of light. So from this is experimentally proven in this Nobel Prize that this life is not real because it violates the theory of the relativity. So this is everything has a pair, and multi-word interpretation theory of quantum says that there is no death, but similarly, when you see to exist on this earth, you will be live in other worlds simultaneously, not a delay of a second. This is the holy Quran when the thorn of the Queen Bilqis was brought with no time. So this is a, we can say, classical example of a teleportation. 1973 Nobel Prize is that this honey is made by the bee that is female in 1973. You see the Quranic siga, ittakhzi, kuli, fasluki, all are siga female mentioned in the Holy Quran. 5 stages of the baby in the mother womb. Dr. Kithamu says that is unbelievable. 1400 years back, there's no was this spectroscopy or something else that discovered. So you see his statement that he acknowledged that this is a book of Allah. Similarly, this is the Nobel Prize 1912 that the uh, Jebel, that is the mountain that are the stabilizer on the earth. And this is that iron is not the product of this earth. This was revealed from the other planet. So this is mentioned clearly. Anzalna al-hadida fi al-basa. These are the benefit for the humanity. Okay, the Big Bang theory, the origin of water is everything is of water. Then expanding universe. These are the latest phenomena of the world. So it was discovered recently that the pain receptor in the skin, not in the flesh. So this is mentioned in the Holy Quran that we will give another skin so that they can lezupul azab. They will feel more pain. This is the, you see, body circle that is mentioned in the Holy Quran also. This is the Nobel Prize. And recently there is a discovery that brain hemorrhage normally occur at the last time slot of the night. So it is better to get up and move. This is the latest scientific discovery. Now you can feel the importance of as-salatu khairum minan nawm. I was in UK. There research was going on whether this ant is made of a some glass material, because this upper component is that upper portion is that major component is that silicate. So silicate is actually major component of the glass. From where this research came? Because this in Surah Namal, when the army of the Hazrat Sulaiman war came across a valley, the queen aunt say, okay, go inside, otherwise you will feel a death. The word used is not dammarna, that is la yahtimanna. So Arab scholars say why this word is used la yahtimanna. That is exactly matched to the one of the property of the glass. So you can be break into pieces. So oceanology, this is the domain. Fingerprint latest technology, that is our memory is not stored in a single cell. Every cell of the body that is stored. And this is the unlimited memory of the brain. But it is not a book of science. This is a book of science. So this is you see one of the phenomena in one aya. There are the the creation of the heaven, earth, and the alteration of the day and night and ship sailing. If you visualize these phenomena, if you digitize, fully understand these phenomena, it digitize, the system will become out that is we known as a artificial system. So true definition of the AI that understanding the sign of Allah for the benefit of the humanity. Similarly, in the cryptology, we can see the hint from the Holy Quran, but this is for the guidance of the human being. And there are a lot of beautiful parameters mentioned in the Holy Quran for a beautiful and peaceful society. Knowledge is one of the major one, but acquired knowledge that we are acquiring, we are getting, but there is a revealed knowledge. This technology will be go in a wrong direction if this is not under the guidance of this revealed knowledge. So our acquired knowledge must be under the revealed knowledge, otherwise it will be disaster. Lot of Muslim scientists they accepted Islam after the study of the Holy Quran. Okay, there are other parameters also, but Quran you see most emphasize on the virtual, spiritual realities, angels, life after that. This is the unseen world. So our quantum world is also an unseen world, very organized life pattern in that. This is a qubit ocean, beautiful scene inside the atom, but it's a paradigm shift. So its behavior is entirely different from the classical one. It does not follow the normal classical principles. Classical physics that is follow the basic fundamental reality. Anything exists that is it is exists independent of the you see or not. But quantum technology that is not believe in that. This is deterministic, that is probabilistic. Secondly, locality, everything will be affecting each other with the maximum velocity of light. Velocity of light, but in quantum technology, in case of entanglement, that is not obvious. So you see, this is a great success of this classical technology. 5 MB, I think 40 years back, it was loaded in the truck, but now you have in the pocket. So a lot of gadgetry in our mobile. So, but it has a limitation. So you can, let's suppose the guests are 10, then there are the probability you see that is higher probability how to arrange these guests in a different way, permutations. But gradually, if we increase the number of guests, this is not possible for the classical physics. Similarly, just move are so much that cannot be simulated in a classical way, even supercomputer, DNA. So even one molecule of a caffeine having 10 raised to 4 bit, that is not possible for a supercomputer. But it is possible with 160 qubit, and we have a more than 1,000 qubit. So quantum has a like a classical system, it also have a structure of different layers. So a lot of organized spended, lot of money in that, lot of technology are evolving in this domain. So physical qubit, but there is this challenges also. Physical qubit, lot of physical qubit, maybe million of physical qubit need to be one logical qubit that is used for processing. So with this technology, Shor algorithm, we can break the classical algorithm. From global algorithm, we can unstructured database, we can easily fast our search. So Jose algorithm, we can computationally you see the power of the this was the first algorithm that showed that quantum computers that is superior than the classical computer. Quantum simulation, we can much faster in this technology. So 2 raised to 30 simultaneously state with only 300 qubit. So you see the processing power. They are instantaneously because of entanglement, no delay in time, communication can be paused. This is the China's missing case that is 1200 kilometer or 1500 kilometer they have communicated through entanglement. Then unhackable, this is the data cannot be copied. So this is an unhackable technology. In what a supercomputer cannot do in 100,000 years, it can do in a 200. This was demonstrated in a Google's Sycamore 53 qubit with in 2019. So it can simulate within a days. So a lot of application in medical sciences. So GPS, no need of that in this technology. So challenges are decoherence is the most challenge, and there are a lot of error correction, limited algorithm available. So a lot of challenges are there. So if you see mathematically, a lot of is covered already. Data math is the next step that will go in detail. I will just skip all these things, just show you. Then we will come towards the post-quantum crypto classical one. So basically, our point that is more intensive mathematics, quantum mechanics, and computing. That is the composition mostly. Okay, these are the property of quantum. This is a linearity of the quantum. This is linear. If you have a two system, so if you add or subtract system, you have another system. The system is linear. Necessity of the complex number. This is based on the complex number. So you can point any point in the complex on the wave using this one. Complex number is actually base of this technology. This is the probabilistics, superposition, teleportation, these are the specific things that cannot be happen in the classical. No cloning theorem, you cannot copy, then every circuit is reversible, then the concept of locality, reality, we have seen. It's a qubit form. Every qubit is traced on the block sphere. Dr. Hamad will cover it. So every circuit we can have a matrix of every circuit phase angle we can represent in a mathematics form. So this is a position, superposition can be represented. So this is the general form of the qubit. Okay. Okay. So single qubit can be represented with the probability of the happening of 0 or 1. So if two qubits, you see the channel capacity, the number of qubit processing power will be increased. So with 50 qubit, 2 trillion bits, you can see 50 qubit, how much processing power, channel capacity will increase, absolute security, so more efficient. So this is a estimate mathematics expression. Okay, no cloning theorem. So this is a teleportation diagram, how we can teleport a one qubit to this diagram. Then quantum dense cozy, we have a two lecture on that. So one photon is ideal for carrying 1 bit of information, but one qubit we can easily send 2 bit of information. So you see capacity can be doubled through quantum. Okay, PQC, this is a classical one. So this is actually algorithm that can save from the quantum attack. So in crypto world, nothing is safe. AG crypto is very famous. You can search on the Google Rubicon operation by the NSA, National Security Agency of America. So that chip having a backdoor and detected, I think, in 2018. It was started in World War II. Okay. So currently cryptography is facing with the Shor algorithm, threat of Shor algorithm, and to little extent to the Gruber algorithm. But AES, these are a little bit safe, but Shor algorithm, this is a hype creator that this can be broken. So this is actually because cryptography used in our all applications, our blockchain, medical record, top secret messages. This is the Chinese paper, say 24 authors that they can break this Shor algorithm. Shor algorithm is a efficient one. What the classical take 10 raised to 20 steps, it can solve within a 10 steps, 10 raised to power 10 steps. On classical terahertz computer, it will take many years, but on quantum terahertz computer, it will be less than 1/6. So you see the commutation. So brute force attack will be very easy. Okay, post-quantum cryptography algorithm that can secure and guess attacks by both classical and quantum. So NIST has introduced in introduced the standard in 2024. So this was the competition was run in 2016, and they are finalized in 2024. These are the four algorithms they have finalized. Okay, this is the Kyber one. So this is actually for the more secret message. So the more secret messages they have required. We have Alhamdulillah made this is 1280 by changing the mathematical model. So we have made another algorithm that is 1280. Okay, this is actually based for the this classical post-quantum crypto that is based on the group ring field, mostly use ring or field. You see, it is used in a classical crypto, Diffie-Hellman elliptical cryptography, RSA, and post-quantum crypto normally let us with ring topology, and this is the symmetric hardware that is AES, secret sharing, etc. So these are the, and you see this is a group is more general form. This is vulnerable to Shor attack, quantum resistance, this is a quantum resistance against Gruber algorithm also. So group is that this is a set of the members having the following properties, closure properties, associate identity or inverse properties under one operation, addition or multiplication, and used in different crypto system. This is a example of the integer modulo 4. So you can add these with number, you will be get the remainder of that element. For example, 3 and 1 is added, that is 4. Modulo 4, it will be 0. Have you idea of that? Okay. Similarly, this is restricted one. So this is having the same closure associated property under two operations, addition and multiplication, but it is not necessary for the, there is a multiplicative identity is not necessary here in this ring. All right, these are the some examples that is with respect to addition and multiplication. And in a field that is more restricted, it is two operation, but every non-zero element must be have a multiplicative inverse. So we use the that is a primitive polynomials. It is generate itself. All elements are generated in it. Okay, this is another concept in the matrix multiplication. In matrix you have to multiply every column with the every row of the other matrix. So a lot of multiplication of step are there. So complexity level will be that is order of n square. Whereas in entity, every element of one matrix with some operation of with omega, that is a unity, nth used of a unity. Every element of this one multiply the respective element of the other matrix, not multiply with 4 row with the complete column. So 1-to-1 multiplication. So this is one of the examples. We have a P and Q matrix. Then we have one of the C matrix. Then we multiply with the Q matrix, and our result will be shown in this form. This is a matrix multiplication, row and column. And but in entity that every element will be multiplied with the other element on the same position. First element will be multiply of the matrix on the first element of the second. Second one will be with the second with some operations. This is a small example. This is of degree 1. If you see this is 2 and 1, this is a matrix, element are 2, 1. This is if you go for matrix, it is order of NO2. But entity, you see, we have a modulo P, omega is selected at 4, and number of element that is 2. If you go for this one, this will be this omega operation, it will be into 3, 1. This is a omega operation. This is the matrix 2 plus 1x. So omega is selected 1, 4. So you have a 4, 1 because this is a modulo 5. So you have a 1. Similarly, for 3, this is the omega 0 and omega 1, these are two values. So when you substitute, you will have a element 3 and 1. Similarly, for other matrix, and these two matrices you see, it will be multiplied. 3 will be multiplied by 4, that is 12 modulo 5, it has a remainder 2, and then 1 will be multiplied by 3, it has a 3 modulo 5, 2, 3. So we will take on the same line the inverse, and we will generate a same matrix. You see, this is actually matrix. This is a 2-degree matrix, 7 integer of 7, a ring. This is a ring. So if when you will divide it, so you will get this matrix after doing, because this is x square minus 1, that will be x square 1. So this matrix actually it will be reduced. When polynomial is multiplied with polynomial, lot of degree will be increased, lot of coefficient will be increased. So more processing is power required. But in entity, we required only small steps, less number of that is operation required. So modular, that is the famous, that is the actually, if we defined, this is the properties. Modulo addition, that will be equivalent to this one. You add, then divide with 7. So you will get a remainder. This is a basic definition. This is you see in the RSA, in the Deppy-Hellman. This is the H function, and this is the digital signature. This is a Chinese remainder theorem. So complexity of the modules can be calculated. All right. This is a very simple example you will find on the net. So RSA algorithm last time has explained every aspect. So we use this one P and Q prime number, then multiply one to generate a public and private key in these steps. So this was very secure before the this threat, but now this algorithm of PQC are coming in the market. Factorization, small example, that is actually we finding the period, that is to see every after the operation of this polynomial this expression, you have a 1 after 4 step, again 1, again 1, similarly 2 after 2 and 2. So the period of this polynomial, if you this function is 4, so it is a periodic function. So with the normal factorization, we can easily find the factor of these three. This was in the last lectures. Dr. Salisbury also explained this one. So latest cryptography, this is actually ring polynomial of degree n. Probably n is selected 256, degree of 256, modulo that is 3329. So this is actually how we compute the key. That is the T. This is a ciphertext. This is the matrix A, and this is a secret key. This is actually error we have added in this one, and modulo Q, that is 3329. So you see, this is actually with simple example we can explain this one. But in actual form, this is the every element of the polynomial, that is 256. So this matrix, every element in the matrix is also a polynomial of 250. You can imagine the complexity of this matrix. So similarly, when we choose a secret key, this is a one column, but this is the every row is that is of degree of 2, but this is selector one, not a complete polynomial. Similarly, we add the error is added, that is also a polynomial of 256 degree. So this is actually complete encryption project, and that is encryption mechanism U and V, two ciphertext was generated. Then decryption, we go for this operation and we can generate that message, original message. So this is actually what we have. This is a key generation mechanism, public and private key, and this is the 31685 private and a public key. And this is actually how public key is encapsulated, because there is a threat also a public key can be compromised by brute force start, because we have a secret, some the text of public keys can be revealed the secret key. So this is encapsulation. Then we have a random key, that is, this is the key that detonated. This is ciphertext and private key decrypt this one and generate the original key that is given to some symmetric encryption mechanism. So we have made, this is not online exist. Only key generation mechanism is exist on the, we have a complete encryption mechanism. Key generation, then we have a symmetric software, that is a crypto system, and we make a complete mechanism for encryption. So we have achieved this level of security 5, maximum security, through these introducing these steps. So this is a Alhamdulillah of first in indigenous made. So we have placed this in encrypted USB. So this is the indigenous effort we have because this is the when we have studied mathematical model of the 1024 of Kuiper crystal, there is a backdoor. We feel that can become intentionally or unintentionally. That can be compromised. We have first of all that take that relationship, then we have increased the mathematical model. So Alhamdulillah, we have a product that is under evaluation. We also working on the cryptech Medicare. Using the quantum machine learning, we are making some diagnostic through classical first of all, then we are giving that data in the quantum machine and analyzing what is the difference between that. So up till now, classical with quantum has some noise. We are not getting the actual benefit of the quantum machine learning, but we are making efforts, or we can get a best result. So this was the last one. I want to say this is a wonderful country. I have visited many countries, America, UK, France, Spain, and believe me, this is the best one. A lot of blessing is there. Definitely mismanaged are there, some mismanagement and some resources not fairly distributed, but till then, I visited Switzerland, no beggar there, filthy rich, but main dilemma is that young lord committing suicide, and demand is so much, they have made a law on that, so you can apply for the suicide saver, because actually they are only worldly life, they are ignoring the soul. And when you are ignoring the soul, darkness will be increased. When it crosses one of the threshold, then no power on this earth can save him from suicide. I went to New York. Light was off only for 3 minutes. Store was empty. So this is the morality. There are so many good things, but to Google for the dark side of the America, you will come to know that is horrible side. So this is a wonderful country. Okay, thank you. Any question, please?
Okay. If there are any questions, please go ahead.
Yes, please.
Why don't we challenge this model? Why we treat this as a law? Basically, the concept is short algorithm translate factorization problem to a quantum phase estimation problem, right? So phase estimation is itself a challenge. So we take advantage when we apply inverse Fourier transform, etc. So why isn't that the quantum phase estimation is credited more than the Shor algorithm? Because eventually Shor algorithm is using the application, is just an application of the estimation.
Okay. Actually, if you go for the classical Fourier transform, definitely you are sum of all these states. But when we are talking about quantum Fourier transform, so every state will be superposition of every state. So computational power will be very high. So it is very easy to find the factor through that. If we implement with the big numbers and there are stable qubits are available, so this is a true threat. But the biggest challenge is that we're not having a stable qubit. So quantum Fourier transform that is a much powerful as compared to classical one. As a qubit, I have defined and classical bit. So your power will be very much increased. So commutation, because of the increase of this computational power, so you can easily increase them. Yes, please.
डॉक्टर साहब अस्सलाम वालेकुम। डॉक्टर साहब थैंक यू वेरी मच फॉर द डिटेल प्रेजेंटेशन। मेरे एक सादा सा क्वेश्चन है कि हमारे मुल्क में तो जो कंप्यूटर्स हैं वो क्लासिकल कंप्यूटर्स हैं, नॉट क्वांटम्स, और हम उस पर सॉफ्टवेयर बेस्ड क्वांटम्स कंप्यूटिंग अप्लाई कर रहे हैं। एक दूसरा सिनेरियो ये समझ लें कि अदरवाइज जैसे यूरोप या बाकी जगह पे क्वांटम कंप्यूटिंग है जो कि बाई मॉडल सिस्टम काम कर रहा होता है, उसके ऊपर वो क्वांटम यूज़ करते हैं। तो क्या कोई फ़र्क है दोनों में कि हमारा सॉफ्टवेयर क्वांटम बेस्ड हो जैसा अभी हम यूज़ कर रहे हैं, और मशीन जो है वो क्लासिकल हो और अदरवाइज?
सर नहीं, ऐसा नहीं है, क्लासिकल नहीं है। हम भी सर जब डाटा सेट को रन करना होता है तो आईबीएम के जो क्वांटम कंप्यूटर है उसको सब्सक्राइब करते हैं 10,000 को $100 और इस तरह से पर मंथ सब्सक्रिप्शन है। फिर हम अपना कोड वगैरह जो है उनके जो एक्चुअली कंप्यूटर है जो न्यूयॉर्क में और इधर उधर प्लेस्ड है वहां पे रन करते हैं। और हमें कभी अच्छी खैर की खबर तो नहीं मिली, लेकिन इंशाल्लाह वो भी मैच्योर हो रहे हैं तो बेहतर मिलेगा इंशाल्लाह। सर
थैंक यू।
Well, our next speaker is Dr. Hamad Tanveer Saab. Well, Dr. Hamad Tanveer Bhatt completed his PhD in computer science from Technical University Kaiserslautern, Germany. And Kaiserslautern, Germany is also having very good football team. And he did his master's in electrical engineering from NUST. At NUST, he is leading quantum computing lab. And he's also working in quantum computing, quantum machine learning, quantum cryptography, and quantum sensing. For his excellent work, he has been awarded with Tamra Imtiaz as well. So here I invite Dr. Hamad.
Morning, everyone. I thank Dr. Farhan Saab for giving me an opportunity and having given me such a nice introduction. Some of the introduction you have seen. I'm basically a PhD in computer science. So my perspective today, definitely yesterday and today even, I mean, much of the things have been covered from various perspectives, basically from the physics perspective as well as mathematics perspective. I would have a kind of a blend of this thing and carry it forward towards the computer science perspective, so that you have something new today compared with what you learned last year. Almost there are many repetitions here today in these lectures, but we'll try to. I'll not try to be rigorous because I know. I mean, I hope not everybody is from the physics. How many are from the physics background? Let's sample from this. Quite so many. I mean, and engineering background too. Both the backgrounds. And rest of you, I mean, if you can raise your hands, who are from the neither engineering not the physics background. Anybody? Which background? Which? Chemistry. So almost everybody is either from the sciences. I hope. I mean, what I was feeling was I hope the audience online. We are online today also as well. Okay. So I hope the audience, online audience, I mean, the sample here is depicting the online audience also, and they are also from the science, basic sciences or physics, chemistry, or bio is also welcome, or the mathematics as well as the engineering fields. So I'll try not to be rigorous, but at the same moment, I'll try to be a challenging. I hope so. So this is the quantum ecosystem that we have at the NUST. You have met Dr. Razak already. I am standing in front of you. In the next few days, you'll see more from the NUST side. Dr. Madiha, Dr. Shahid is SNS. He'll probably not be joining this workshop. Dr. Imran has graciously come today. I mean, he's also, I mean, he is working with us on the quantum CFDs from the CFD field, and he is working from the perspective of applying the quantum computations or the quantum algorithms to the CFD side. And then there is Dr. Faisal Shafas. He's also from Germany, PhD from Germany, from the same TU Kassel University, and he is helping us with the machine learning side, quantum machine learning side. So this is a short, I mean, visiting us quite often these days as a quantum technologist. And Dr. Sabi is not here today. He was yesterday. I mean, he probably will be taking the last day. He is from the Nilo. He's also, I mean, there in the NUST and joins us quite often in discussions as well as, I mean, mentoring the students. This is the overall framework that we thought once we started this quantum computing lab at NUST. We wanted to expand this into an ecosystem called GUIDE, which is basically an acronym for the quantum advantage for the certain stage, maybe though I think that in scientific computing it will always be a marriage of the supercomputers or the computers and the quantum computers. You will never be able to, I mean, completely get rid of the classical computers in some certain sense. So the approach I'll be following is, because it's a workshop, it's not a coursework. Normally, what we do in the coursework is that we build from, I mean, bit by bit, and then we complete the complete picture. What I'll try to do here today in this entire scenario is to throw everything on you. You will get a very vague picture initially. That is my style of the workshop. You like it or not. I hope the people coming next to me, they have a bit more, I mean, favorable kind of approach, as you have learned in your, I mean, universities and the classes they build by one by one, brick by brick. What I'll try is show you a vague picture and then try to, I mean, make it more visible by the end of my lectures. So things are more clear by the end of the lectures. From the rougher view to the more refined. So this is a small quote. I think that, I mean, I hope there are no international audience, but I can, I mean, I can translate it for them, because new foundations can only be laid by the people who know why the old foundations have gone down. So this is a quote from Mukhtar Masood, I think Awaz-e Dost book. And in Urdu, you can read it yourself because I think everybody is Pakistani, not international. There is no international student today. Any international student today? Online, okay. But I mean, just translated this for them. So how we reached here? So I'll try to connect it with the AI. Because you see, the AI was there for quite some time. Since 1950s, the idea of the neural networks and the neurons and to replicate them in an artificial way was there. But and even the algorithms. I mean, as I remember, once I took the field of the AI somewhere my bachelor degree way back in 90s. AI was entering the second summer at that time, and the main problem at that time was the hardware. There was an excellent software available at that time, for which the Geoffrey Hinton is awarded the Nobel Prize also. If you have heard of him, Physics Nobel Prize for his gradient descent. Everybody use the gradient descent these days, but it was invented somewhere in the 80s. It was available to train the multi-layer networks, but the main issue was the computational power, how deep we can go. So everything changed by repurposing graphical processing unit, which are basically invented or manufactured for visualization purpose, not for the compute purpose. Indirectly it was computing, but it was computing for the purpose of the visualizations or the graphics. Once it was repurposed, the same math, the same matrices were repurposed to do the AI. We had the marvelous domain of the AI that we see today. Many of you do not know, because you have seen the AI. Today you cannot imagine how it was back then in the days of 80s and 90s, once we were working on the AI. So today, with the GPUs, you see marvelous results coming, but it was almost impossible to replicate or even generate those results in those days with small processors, CPUs, which at that time were not having even the cores. Now you have CPUs with the multi-cores. At that time, it was a single core CPU that was working, and it was almost reaching its peak. So basically, it was the invention of the GPU that made everything possible, the AI revolution. But now what we see is that the GPUs, with the current foundation model that we are generating for the AI, they are reaching their limits. You can see the current foundation models, which include both the vision models as well as the language models, they are almost it's already an exponential scale. The vertical scale is already an exponential. So you can see that even on the exponential scale, the rise in the power of training cost is exponential itself. So it's an exponential on the exponential scale, not a linear on the exponential scale, which is itself an exponential if you linearize the scale. So this scale is already, sorry, no pointer? Last question for Acha. Okay. So this is where the limitation of basically the GPUs is coming. Thank you. So this scale I'm talking about, this is already a log scale. So on this log scale, what you see is there is already an exponential rise that you need for the computation. So we are reaching our limits, not only in the compute power, because we need a large data centers, very large data centers for this kind of models to work. You use them via cloud. So there was a question to me, I think today, that why we are only doing the quantum on the simulation route or emulation route on the classical computers, and why we need the cloud access to actual quantum computers. The thing is, even the AI or the normal computing is going at a scale where we need the cloud access anyway. We cannot have our own cloud doing these kind of models here in Pakistan. We cannot even survive the electricity cost or the energy cost that is needed for them. So in any way, the future is cloud, whether you get it as a classical cloud or a computer cloud, and definitely it will be somewhere a marriage between the two. So what is happening is, due to the scaling laws of the AI, with the data set as well as the model power, as it grows, we need exponentially more resources. In fact, it is not exactly exponential; it's a polynomial, but still, we can kind of get quantum advantage over here. And more important is basically this energy cost. So, Dr. Deiter, probably, if I'm spelling his name correct, yesterday, Dr. Deiter. Dr. Reiter is yesterday covered this covered this energy part quite well, showing you a basic downward limit of the energy that each switch can reach, the maximum limit that each switch can reach. That is of the order of the Boltzmann's constant into temperature, and that was defined way before once the Feynman first proposed the idea of the quantum computing itself. I mean, this is the idea of the reversible computing, and the minimum cost of the gates was known at that time. So we are almost reaching those limits. And still, this is the limit, by the way. But we are at the moment, we are expending much more energy above that limit. And it is very hard to extract that energy, whatever we are expending in the GPUs, it is very hard to extract that energy out of those transistors. And that is our basic limit, the heat dissipation limit. We cannot dissipate the heat fast enough so that we can run our CPUs or the GPUs or the data farms at the right for the right compute power at the right speed. So that is basic limit. And our algorithms and the models are growing in the complexity. So with this, there is algorithmically and from the computer science perspective, there is no way, I mean, that the transition would not happen. The migration is inevitable, not only from the physical perspective, but also from the computer science or the algorithmic perspective. So that is for sure. I mean, what kind of, this future will be, whether it will be totally quantum, it will be a hybrid of quantum, it will be a quantum tech enabled, that is a question mark. We can discuss that. But the problem is that we are reaching the physical limits, we are reaching the algorithmic limits. So somehow we have to have some compute power, just like GPUs. Now we have to have a jump. Unless we have that jump, we cannot sustain our current rate of growth of the computer science, computer technology, and as well as the AI. So this is our main problem. Now let's focus on one another aspect of the AI today. These are 3 steps. I would, if everybody has a mobile or a laptop, you can open and you can try step 1, 2, and 3. The step 1 is choose any 2 11-bit numbers and multiply them on the calculator, simple calculator, regular calculator, which is there on the mobile, most of the mobiles and even on the laptops. Open it. Let's do an exercise. Anybody who has done this experiment before with me? Okay. I hope the result stays the same. They have not invented some workaround after coming to know that there is a loophole, a gray area. 11-digit number, both should be 11-digit numbers. Multiply them on a calculator. Save that thing in a separate window or a note. If it's a mobile, note it on the exact number on a notepad on your notes. And then I request you to multiply those same numbers in ChatGPT, which is an LLM, or the highest kind of the marvel of the AI that we today think. So open the ChatGPT window and try to multiply these 2 numbers there. And once done, you can raise your hand so that I know how many people have reached that step 2 and completed it. Anybody done with the second step on ChatGPT? Okay, anybody who has done it, just raise your hand. I think, okay. So you have done it, Seth? So is the result same? The 2 results are same or where they're different?
4 decimal.
Okay, anybody else whose results is same, exactly same on the calculator and on the LLM, on the ChatGPT and the calculator, exactly same result. Those who have exactly the same result, raise your hands. 1. Anybody else? I mean to the last unit, same result. Have you checked it? To the last unit, it is same. Okay, 1%. Anybody else? Only 1% change. It's a sample, so we can expect anything to happen because we are doing the sampling here. Normally, it's not a large population, but normally what I expect after second step is a 50-50 result. The 50% should get the exact same result and 50% should get some difference at some place, starting at some place. On a large population, it would be like that. But right now, if I is completed, only one person is showing that he has results. Anybody who else claims that anybody else claims that he has the same result on the calculator and ChatGPT. Everybody done. Raise your hand who has not done it. Anybody who has not done it. You say result. Two. Do we need this? Do we need this, or I mean, I can be audible just by talking. I'll be audible on the online. Is it needed? It's needed. Okay.
Online.
Okay. Because it's creating trouble for the audience. So. Okay, so 2% have got the same result. In first 3% have got the same result. In I mean audience of participants of maybe 50-20, I expected 50-50 at least. But I mean it's a sample, so randomness is always there. 33% still got the same 100% same result. But those people who didn't get them, most of the people didn't get the same result. Just make a hypothesis. What was the reason? It's an AI. It should work. Why it is, I mean, getting flopped here on a simple multiplication of 11 digit numbers? आपको तो पहले पता है. You have already attended a workshop, so you can tell. Okay, you tell. Say, Saf, you want to tell or Arun wants to tell? Saf wants to explain. Okay.
Always learn from fact. AI is fact.
Okay. Anybody else who wants to add to that? It's a big, from my perspective, it's a bit big explanation. Even after having attended this workshop. Anybody else? No. So I mean, nobody has made a guess, but it's exactly making a guess. The AI basically predicts by probability. Your LLM learns the probabilities. It is just once you give it a string of the numbers or whatever you give it, it is just trying to predict the next number with some probability. Once you make your string long enough, that prediction starts to fail at some place. Although, I mean, there are ways and means in which AI can address this, and they are doing it, but they are compute intensive. Like there is a way that's called inference time compute. You make multiple guesses, but that is compute intensive. There are ways of agentic AI. If I mean, it's not a simple LLM, it's an agentic LLM. Probably ChatGPT also has certain agentic features, but they have not at the moment. They have not introduced the agentic AI for this. So that's why this flaw is still visible in experiments. And this is just one flaw. Similar flaws can be found. This is just one clear example of the flaw, which indicates how AI basically works. So all AI models basically work on the probabilities. They do not work on some clear-cut deterministic algorithms. That's what the AI is doing. So why not use something that already works in the domain of the probabilities? Why to spend time calculating every possible outcome randomly, generating a complete sample, and then coming up with the probability which is not exactly correct also, or approximate most of the times. Why not to move up to a field or a model, computational model that integrates the probabilistic aspect in the model itself, and that's where the quantum helps. This is what we do with AI these days. We are basically having a lot of data which has the divergence or sample mean or sample distribution at every point. What we learn from this data is a straight line. Normally, in the regular AI, we try to fit a straight line in this. In simple regression, we try to fit a simple line in this. By fitting a simple line, while we are reducing the overall error, we are letting go of these probability estimates at every point, which we are not learning. What if we can, actually our model can give these probability estimates at every point? And why not? That is where the quantum machine learning enters. For me or my own PhD work, the quantum machine learning was not about having some kind of advantage or supremacy. In a way it is a supremacy or advantage, but in the particular case of statistical distributions. Because here, once you need statistical distributions, the compute cost becomes, for regular AI model, compute cost becomes too heavy. Even the classical methods which do not use the AI, like the particle filter, they almost, go neck to neck by working this out. So quantum or quantum machine learning or the quantum algorithms are a favorable choice in these kind of scenarios. Once you want to predict instead of getting single number or deterministic answers, you want to get the probabilities, because probabilities are better than having the single answers. You have seen, you try to get a single answer from the LLM, and what it did to you have seen. If you try to get the probability, probably you will have the probability with some, you will have the right answer with some probability. You'll find it somewhere, right? With some probability that will also appear. But here you have seen that you have, taken a single number at every point from the distribution, and what happened was that your AI model failed at simple multiplication. Okay. I'll just skip over certain things because yesterday people have talked in very detail about them, but just a bit of, we can represent everything by mapping the problem onto a symbol, and our symbol is basically a byte. We can map our problem, any problem or problem domain, onto symbols, and then we can define the rules of manipulating those symbols, and that is exactly what the computation is, or digital computation is. If you compare it with the analog computation, what we do there is that we simply translate from one domain to another domain by using the analogs of the quantities. For example, if I want to calculate the force, I'll just use the voltage in the electric circuits. If I want to calculate the velocity, maybe I'll have an analog of current in the circuit. In the analog domain, we have the continuous thing mapped continuously, but in a different set of quantities. What happens in digital computation, we define abstract numbers. That's how we learn the mathematics since our childhood. We have the numbers, but what we see as numbers are basically abstract quantities. They represent something. The numerals basically represent something which is a concept, which is number. You have designed the numerals, symbols for them, and that's how you perform the computations, step-by-step algorithms, multiplication, addition. Exactly, that's the same way we perform the digital computation. We allot the numbers, although those numbers or symbols are different now. They are ones and zeros, because for computer it is easy to manipulate those, having switches or the transistors. So now the symbols are different, or their abstraction is different, but still it is doing the same job as you used to do, or still we used to do in our daily lives, calculating something by algorithms, by translating them to the symbols. So there are two ways to do the computation, and both probably can be done in the quantum domain also. But right now, mostly we focus on the quantum digital computation, which have the qubits and it's in a way you'll see that even these qubits are basically somewhere in between. What I'll show that if they are also in between, they are somewhere in between the regular bits and the analog domain, because the operations on the qubits you'll see and the superposition you'll see they are actually in the analog domain. So how a regular computer solves these problems? Basically, we have a state inside the computer which keeps a memory of whatever we are doing. It's kind of like you are performing some computation. So you are jotting down some things, some carries and everything on a paper, pen and a paper. It's a kind of your memory slate. Similarly, if the computer has a memory slate, and what we do is we provide the inputs one by one, and what algorithm does is algorithm takes it from the state to state by changing few bits at a time. Algorithms take it from one step to second step, third step, and till the time you reach a stage or a step where your algorithm is guaranteed to give you an answer. If our algorithm is designed to go through all the steps of the algorithm, at the end of the algorithm we'll get our answer, right answer. But it's all deterministic. Every step is deterministic that is happening, right? This is what the classical deterministic computation is. Now for this computation, how we perform it, we basically use the logic gates for this. I mean, these logic gates are basically, based on transistors. And the So a program is nothing. Those steps are nothing but execution of these hardware operations. These hardware operations step by step. This is one step. All these steps are happening concurrently. Then this is one step. This is one step. Although we normally ignore this step because we take it for granted that we generated this step. So normally these two steps are counted as real steps. So algorithm is walking us, the state is getting walked through all these steps one by one to the gates till the time we have a final answer. A similar model, which is more universal and which is more mathematical, is called a universal Turing machine in computer science. So what it says is that any deterministic algorithm that we have seen can be implemented in a much simpler fashion with a much simpler set of rules if we just have an infinite amount of memory and we read from that one step at a time and make just one and implement just one instruction out of those instruction sets. In fact, this can be made so lean that only one instruction set is enough to do anything. Just like most of you are not from the computer background, but probably in the physics also you have learned that there is a one universal gate that does the work of every other gate, which is NAND or NOR, right? Similarly, in Turing machine, it can be made, normally the regular concept of the Turing machine or what Turing proposed was not one instruction set, but people have one instruction set is a conditional jump. And we'll see that this conditional jump is there in the quantum computation also. We'll just shortly come to that. So if you have just one conditional jump, nothing else, and this Turing machine, infinite memory, and you perform that conditional jump on the states, which is there in the say RAM inside the memory. The state is kept separately in the registers. From the memory, you read something, you append your state, and then based on that state, you make a jump. And then whatever outcome comes, you rewrite the memory. Just by doing this will be slow, definitely very slow, compared to the computers that we have today, because we can implement a large instruction sets. This computer will be very slow. But in a sense, whatever is computable can be done by this computer. And even a quantum computer cannot go beyond this. From the computability perspective, whatever a universal Turing machine does, a quantum computer does the same thing. We cannot go beyond that. But with a caveat. What can be done by a probabilistic Turing machine, not a simple Turing machine? Because a normal regular Turing machine is deterministic. The steps there are deterministic. If you add the probability or coin toss into that, while making a jump, you toss a coin and then decide in addition to the state, you also include that coin toss in it. So that once that probability comes into play, then it becomes a probabilistic Turing machine, and that is the most universal kind of a thing that you can have. And with that you can have as many problems solved as possible. Even the problems which are solved takes exponential time can be solved by the Turing machine. It is not the fact that they cannot solve. The only problem is that it will take non-polynomial time or exponential time to, maybe many years, centuries, or even age of universe to do that. What the quantum computer does for us is that it makes them fast. This is the basically idea. So here are two examples, simple examples. You have seen the factoring. Everybody has talked about the factoring since yesterday. Its inverse is multiplication, right? Inverse of factoring is multiplication. So if you have two numbers, you can easily multiply them in polynomial time, and you can get an answer, and you can check that whether that answer is correct or not. It's a polynomial time thing. Okay? But if you want to factor it back, if it is a simple number like 6, it is easy. You can have the pick the prime factors just by inspection. But if it's a large number, the prime factoring becomes difficult because there is no set algorithm for the prime factoring. There is a set algorithm even for the square root, for all kind of roots, but there is no set algorithm for the factoring. So what we have to do in case of factoring is we are actually performing a random search, nothing else. A computer does a search, an exhaustive search in case of factoring to find the primes. And once the number gets very big, that exhaustive search has implications. Because there is no other classical algorithm known that can does it better than a comprehensive search. So what happens is that for certain kind of class of problems, their complexity, which is called big O complexity, that grow, or big O is basically order of. So for certain class of problems, as the size of the problem grows, which is basically measured in number of the bits. So as the size of problem grows, the time to calculate them exponentially grows. So these are the problems that we want to have quantum computer for, or we want to try our luck with the quantum computer for these problems. For the polynomial problems, we can also get an advantage. It's not the case that all polynomial problems which are already solvable by the classical computers can be exactly solved by the quantum computers. And in some cases, quantum computer is better also. But that thing is called quantum advantage. What I am talking of right now is for factoring like, what I am talking of is called quantum supremacy. These are the kind of problems that cannot be solved in polynomial time by the classical computers. For them, if we get we work out some quantum algorithms and it works, we call that, we make it work on actual quantum computer. We say that we have achieved quantum supremacy. Short of that, quantum advantage is always there. There is a polynomial problem, AI problem is a polynomial problem. We have seen. But for very large polynomial problems, maybe we can achieve a kind of a quantum advantage if we still use the quantum computers. So this is the difference between the quantum advantage and quantum supremacy. This is the whole class of the problems that we are trying to solve, in which the class which is not shown is here. This is in the polynomial space, but just touching the NP complete problems. It is called NP hard problems. Many problems like traveling salesman problem, which is shown here as NP complete, is basically both NP complete and NP hard. Which by that I mean is that if you want to decide about some path, whether it is optimal or not, that decidability problem is NP complete. That can be done. If we have by NP complete, I mean if you have a non-deterministic Turing machine, a probabilistic Turing machine, you can solve it in polynomial time. You can design an algorithm which can solve it in polynomial time, a decidability problem. But if you actually want to find the optimal path for the traveling salesman problem, that is NP hard. There is no polynomial algorithm known either on the universal Turing machine or the probabilistic Turing machine for that. So if you can hit that NP hard problem, that part using a quantum computer, then you have basically included that problem from this set, from here. You have brought that problem from here to this bounded error quantum polynomial category, which by the way, which can already solve all polynomial problems. But it can do something extra also in the probabilistic domain. And still better, it can do something for the NP hard problems, which will jump from here. If done, they will jump here from here to the NP set and finally land into the bounded layer quantum probability problem. This is a short history of the computer evolution, and we are now reaching this stage, as I've already discussed. So I'll just skip this slide. We have reached the physical limits here. By the way, all this evolution you can see is also happening due to the quantum computing, quantum mechanics. This is not, I mean, quantum mechanics is not irrelevant here for the classical computing. All these steps are basically enabled by the quantum mechanics itself. But that thing is called quantum mechanics revolution 1 or quantum 1.0. Now, what we're trying to do is we want to create a second evolution through the quantum 2.0. So we are now entering an era of the fifth generation computers where we'll have some kind of quantum effects. Even if they are not true quantum computers like we are talking today in this workshop, quantum focus, since this workshop is a broader focus, it's a quantum frontiers workshop. So somehow the quantum effects will be there. Even if they're not be using the qubits, maybe they're using something else. But the quantum effect will be utilized. That is, I mean, as I said, that the transition and the migration is impossible to avoid. These are all the things quantum that you use daily. This is a quantum 1.0 that you are using, and even the classical computers are using. We do not know. I mean, most of the physics students know, but I mean, if the people are from the other domain, they normally ignore that. I mean, these technologies somehow use or they do not understand these technologies. Even simple camera is basically using the CCD camera is using the quantum mechanics. But what we want now is to utilize those quantum effects which are happening at a very, very fundamental level. And those effects are basically the superposition, the entanglement, and the interference. So what these effects are, the second quantum revolution, we want to have the quantum systems which can have some kind of two possibilities. And those two possibilities, that quantum system can exist in a superposition of those possibilities. So if this quantum system can exist in superposition of those probabilities, then we can have a state which has both the components or the bases with some complex weight. Although there is a limitation on these complex weights, that the sum of these complex weights should be 1. So this we want to create, this superposition we want to create. What it does is that if we have, say, n bits and we are doing operation bit by bit, then we have to get each of the 2 raised to power n bits. We have to get each one of the 2 raised to power n bits, and we have to perform operations like I showed you. But if you have a quantum computer, what you have is all the bits. Say, I mean, just imagine coins. If we don't have coins today, and I don't have in my pockets also, but just imagine coins. You have placed the coins on a table, and you are trying to flip them one by one to change the states, right? The second option is all the coins are in your hand, and you are shaking them constantly. So this is the second state. Just analogy, not exact analogy, because it's not a superposition. It's a probabilistic thing that I'm doing. But still, I mean, just try to imagine that I'm shaking those coins. And now on the go, what quantum algorithms are doing? Those coins which I'm shaking, those quantum algorithms step by step are changing so that once I make a final throw, the biases are changed so much that I get the right answer with the highest probability. That is the aim. That is the total quantum computing that we discussed yesterday, we'll discuss in the next days, and even after. So the crux is, you have the coins in your hand, you are trying to change the bias of those coins on the go, step by step, so that once we make a final throw, in least possible number of throws, you get the right answer correctly. It is not that you will always get the right answer, because it's a random phenomena. You can get the wrong answer also. But remember the multiplication versus factoring problem. The inverse problem is always simple. For the NP hard, the inverse problem is always simple. Once you have the thing, you can easily decide whether it is correct or not. So once you have an answer, like 3 or 4 answers, 2 might be wrong randomly. But one possible answer, once you check it, since you are having a high probability, it is very high probability that in first 2 or 3 tries, you will get that answer. And once you counter check at every step, you will soon get the final answer. instead of trying all the possibilities one by one, which happens in the factory, right? So each extra qubit that we add to this mix, once we have the coins and each extra qubit you add and you try to, play them around. Each extra qubit you add, basically that increases your power by factor of 2. That's why you get, for n qubits, you get 2 raised to power n power. So for example, if you have a 64-bit of data at a time in a normal computer, if instead I have 64 qubits, I have an enormous power. It is 2 raised to power 64, which are almost, the computer can become 18 billion times faster, which is, you cannot even imagine, the fastest supercomputer cannot do it. So your computer, the new computer that you have now in the quantum form will get 18 billion times faster. But it is a claim. There is again limitation and caveat to it. We'll shortly see it. How it is done, I'll explain this Hilbert space later on also, but what is happening is here is you can see that each qubit is living on a kind of a hypothetical sphere, which is of the degree 2. It has a degree, why it has a degree of freedom 2 will shortly discuss in the later half. But each possible qubit is basically lying somewhere on this sphere, and it has the infinite number of occupancy points. That's why it is analog also. Although it is a qubit, but since it can lie anywhere on this sphere, it can have infinite number of possibilities with super resolution. What quantum actions or quantum processes are doing, they are moving the qubit around on this sphere, hypothetical sphere. For a single qubit case, it is very simple. It's not a hypersphere, it's a three-dimensional. For a single qubit, it's a three-dimensional sphere, we can easily visualize what is happening. For a multi-qubit case, especially if they're entangled, then it becomes difficult. We'll see. But single qubit case, and any kind of rotation can be performed. This is the standard rotation I'm showing from plus to minus. But even arbitrary rotation, which can be decomposed into 3 parts, which is in SO3 space, can be performed. That's what we do in the quantum machine learning regularly. We actually, encode the data by this kind of thing. Even, learn the parameters. So there is now one extra rule that we need. Apart from what we have learned till now is, there is one extra rule we need. That extra rule is that quantum mechanics or the quantum computation ought to be reversible. Our regular digital computation or the Boolean logic is not reversible. Why it is not reversible? It is taking 2 inputs and it is somehow losing the information and giving us only one output. But what happens in the quantum domain is that if we have the number of the input lines and number of the output lines are same, one line can be simply passed through, while the other line can have some mixture of, say, this bit operated XOR with this bit. So in quantum domain, we ought to have a reversible computation. Why? We'll shortly see. I'll not explain here in the next lecture. Here I'm just making the premises for the next lecture. So this is the difference. Just but I highlighted it. The second thing is, these are the qubits. Actual qubits look like this. I'll cover them tomorrow in tomorrow's lecture hardware also. But actual qubits somehow the quantum processing unit looks like this. This is a qubit. This is a qubit. This is a qubit, and this is a qubit. The rest are just the connecting resonators and stuff like that control this qubit. So these qubits basically, which are Josephson junctions in this case, superconducting Josephson junctions, they carry the data and they sit there idly on the chip. There is no copying. Every operation has to be performed externally through analog signals or microwave signals or some kind of signals, lasers, that has to be performed on these bits. So all the circuit steps you are seeing are happening on these bits, step by step. You cannot copy these bits because if you make a copy, these bits will be destroyed. Of course you can copy. It's not like that you cannot copy. The no cloning theorem is not that you cannot copy. You can copy a quantum state completely. But the previous quantum state from which you copied gets destroyed. It goes in air. Now your next replica is exact copy, but that is only one copy. So there is no fun in having multiple copies. So ideal option is to keep the qubits there and perform whatever you want to perform on those qubits and then get the answer. Whatever is happening in between, you cannot see. And this is a big limitation. Somebody, asked, yes, probably yesterday or today, I think somebody asked online question that, why, we need the classical computers and stuff like that for the exact same reason. But once we want to qualify some quantum algorithms, we have to first qualify it on the classical computer, on an emulator. Because on a regular computer, quantum computer will never see what happens, except the results. If we actually want to see the quantum state, you want to have a kind of a prototype or a smaller version run on a classical computer. If it is okay, if it is doing something, if it is meeting your logic, then you expand, scale it up, and then you go to the actual quantum computer. Because quantum computer's access is also costly. You cannot directly go to the quantum computer and say, I have access to the quantum computer, I'll do this thing. It's costly and it is inadvisable because you do not know what is happening inside your algorithm. First, check your algorithm step by step. If it is meeting your expectations, the states are meeting your expectations, they are performing what you want them to perform, and then go scale them up and deploy them on a regular quantum computer, and then you'll get the answer. That is the right approach to do. You finally get the answer. You gave it a state. Actually, what you gave is a probability distribution, and what you get is a probability distribution. There is a probability distribution in and a probability distribution out. For some cases, for deterministic problems, we map our problem like that probability distribution basically gave us a particular deterministic answer. That is one case. If I want to get only probability distributions, I'll not get this measurement. I'll just get the probability distribution. Or I'll get the measurements, but I'll get those probability distribution. So in that case, I'm interested in the probability distribution. So this is the kind of probability distribution that you get after measurement, after repeated multiple measurements. Here you can see this is some quantum algorithm that has given you a probability of 1 month. These are 4 states. It means you can see this is a 2-qubit probability distribution because there are 4 possibilities. You can see that the possibility of probability 1 0 0 is exactly 0. That means the 0 0 has undergone a destructive interference, complete destructive interference. Even the 0 1 and 1 0 have undergone some destructive interference, that is less. Our answer was probably this 1 month. That's why we tried to increase or do we want to have this possibility with the constructive interference so that we get the highest answer. This is where the interference gets involved. This interference you cannot see. This is happening in a computational domain. What you physically see is the physical qubits and physical gates you are implementing on them. The computation is happening in a virtual domain, in this probability distribution. And this interference is taking place through the computational paths in those virtual domains. Linking as I started, linking the future of, as you can see, this is exactly the relative frequency word count from the Google for the searches or for the corpus which is available, of scientific corpus that is available. You can see that as the AI has gone up and down. This is first AI peak, somewhere around the 50s. Then first AI summer, then around 80s, Jeffrey Hinton time, another AI peak, then second AI summer, and this is the AI now taking peak. And it's not shown further, not shown ahead of 210, but actually, this is now almost taking off exponentially, as I showed you. But this peak is closely followed by quantum computing, as you can see, especially the second peak, because people realized at that time, at the very time that I entered into a machine learning domain, people realized that the GPU will have a final day. At one point we'll have to see them off. We'll need new hardware. So as soon as this realization comes, and at the same time, this cryptocurrency also came somehow. In fact, the AI limitations was less visible at that time. Cryptocurrency was the more hard hitting point at that time. That we have to solve certain problems really fast if you want to break the crypto, because otherwise the regular sovereign currencies will have their final day. So heavy investment came into quantum computing, but it is closely following the AI and deep learning curve. This is the first part of the lecture. I'll not do break. My stamina is, quite a lot. I hope if somebody wants to take a break, he can go out anytime. But in that break time, I can have questions. Any questions till now?
We have 5 minutes for questioning, answering. And then
we can take a break also, by the way. This 5 minutes of the break and question answers.
Well, the break is there because at 1:30, as I told here, that is namaz available.
Yeah, sorry.
So we can offer namaz at 1:30, and then after that we have lunch. So we have good break, and then the next session will start around 2:15.
Okay, sir.
So we have that with us.
So thank you very much.
So any question you have?
Yes.
Sir, in quantum we have probabilistic following probabilities, but to get the exact answer in probabilities, we have to repeat the experiment infinite times by the law of large numbers. And the example you showed just now about 0, 0, 0, 1, and we have 50, 50, 25% probabilities, and then we had 50% probabilities. But we have, what if we repeat the experiment for the next time and next 1,000 times, for example, the probabilities of the 0, 1 and 1, 0 will increase. So how do we get that this is the exact answer?
The probability will almost stay the same in this case, but it is a very bad example that I showed you. Because remember the destructive interference should stress all the other possibilities, and only prop up the constructive interference should only occur on the right possibilities. So the example I showed you is a bad example, frankly speaking. If you want to go through this further, I would advise you. There's a recent paper that published in NPJ Quantum on the quantum cryptanalysis of the XPN ciphers. Go through that. We exactly deliberated on this point, and the reviewers were skeptical, but we actually showed them that how it is happening. Because people normally go for in case of the algorithm, basically we go for the theoretical limits. That if the total search is taking the 2s per n, then the quantum advantage in that case is only under 2s per n. But what we showed in that is that if you do the experiment even lesser number of times, you have a fair enough chance of getting the right key. Right? So what is important is you need to have a fair amount chance of getting the right key. It's not a theoretical thing. If you're doing something practically, if I want to utilize something for the practical purposes, even if I have a fair amount of chance that I repeat the experiments 10 times, and at least one time I'll get the right. That is enough, because I can always cross check the keys. Which key is correct? Which factor is correct? Right? That is easier. Any other question?
Sir, I want your comments on one understanding of mine. You have mentioned about AI and optimization and etc. So I have understanding that there is no universal algorithm exist which gives exponential speed up for database search. We do have Grover, but it is quadratic speed up. So why isn't in anywhere in the world? So we are not doing a research to have an exponential speed up algorithm which same like Shore. So why we have stopped at Grover? So that is my
answer to that question. The thing is, yesterday I would beg to differ. That brings me to the point of the yesterday's discussion. You reminded it. I wanted to discuss also. One point about the Dr. Sunil Berry. He is definitely a luminary. I cannot contradict him. His talk was really eye-opening for me at least. But I had a question at that moment, because you see, there the measurement is taking place somehow. But what is happening is somebody is blocking the path. Actually, even if the photon comes to know that it is blocked, right? So what if I'm sending the photon to say, ratio of the photon is very less. But if it is a long fiber optic, actual channel, actual quantum network, there will be extinction. And the extinction of a photon, which is a random phenomena or probabilistic phenomena, always happens probabilistically, but it is somehow blocking. Photon is getting absorbed somewhere. So we can Grover algorithm is nothing but a brute force approach. It's a brute force search, but parallelized in the quantum domain. There can be a better algorithm than that. And perhaps one way forward is by linking the AI with the quantum. Because through AI, simply from having a large amount of data, we can learn new algorithms. That's what in the classical domains the AI does, where we do not have a set algorithms. The AI gets the data and just make a model for us, and that works fine. Why not utilize the same approach in the quantum if you want to search for new algorithm, or be smart enough and propose one? Grover and Shor is not the end of a journey. They are very old, and they just simply showed that the quantum works. Go beyond them, think beyond them, and we do not have programmers for that.
Well, we have one question online, and then we.
Okay.
I think it's there. Is there any role of entanglement in quantum computing?
Yes, sir. There is a role of entanglement. I will discuss just after the break.
Okay.
There is a lot of role, and we'll discuss just after the break.
So here we stop, and there is one more question. Just a quick question: will quantum computing make cyber attack easier or harder in the future?
This is just too vague an area to comment at that moment, because I said that there are not enough programmers, and people have not came up with a killer application or the use cases. So frankly speaking, I find it hard to forecast the future in that sense. But definitely, like if the cybersecurity keep banking itself on the classical approaches, then yes, definitely. The quantum computing, the advent of quantum computing will make it compromised. Even for the algorithms for which the Grover is the key, right now the only answer for the AES. Maybe we are able to find algorithm better than the Grover that will.
Now we have the ready. It's at second floor, so we have this room available for this, and then immediately after that we have lunch, and at 2:30 we are going. At 2:15 we are going to eat.
Module. So here will, I'll not be very rigorous, but here will use a little bit of linear algebra. I hope the people are comfortable with that. Physics people should be comfortable, even the engineers should be comfortable. If they are not, they haven't done the right engineering properly. So because this will be very simple, and I try to keep it simple also. So first of all, a little bit of notation, right? Some will carry forward some certain things from the physics. Beyond that, I'll not assume anything physics in this lectures or in the lectures today. Maybe tomorrow we'll need some physics for the hardware implementation. Today I'll not need, except these two notations, which are draw and cut. I'll not need any other physics. This is the only thing that I'm carrying forward. That the Dirac notation is the only thing that I'm carrying forward from the physics. Rest is simply mathematics, which should be known to everybody who has done some basic science. So, we can represent or we can associate with these Bra and cat notations the vectors. The Bra is normally a row vector and the cat is a column vector. And this terminology is again, this is implemented like that in the physics also. And if we write this Bra and cat like this, right? This option where the Bra is being followed by a cat, then this represents a dot product. That means a row vector is being multiplied by a column vector, right? A row vector is written first, then a column vector. So it is a dot product. The whole row vector multiplied by whole column vector give you a one number. Which, by the way, I'll show you. This number is basically decomposition or projection of one vector on the other. And the second option is if I reverse the order. First I write the row vector and then first I write the column vector and then the row vector. This one. This is called outer product, and this is basically generator operator. There are every kind of operator is possible. Here I am just using the same state. So I mean this will be a this will be a qubit representation. This thing is a qubit representation, also outer product. But if I change the size, I mean, for example, if one is psi and another phi, I can generate a number of operators by this. And if I multiply two column vectors, I mean two cats together like this, I can simply, this is a tensor product, and I can simply combine all the possibilities. So these are all the possibilities that can happen. And then the second part, apart from the linear algebra, the only probability you'll need probably is that whatever is happening in this through linear algebra, once we try to measure it, it transforms into probability distribution. That is the only information we need for the entire quantum computing. Maybe I mean at an advanced stage we need more, but for startup or starting purpose, this is enough. And then there is an abstract algebra. I'll just touch it because those rotations that you are seeing are basically SO3 group. They are called SO3 group. Those rotations that you are seeing on the Hilbert sphere that I shortly showed you for a single qubit, they are in the SO3 space and their group. Just I mean hinting that. Ahead of that, if you are using quaternions can also be used for quantum mechanics. If you are using quaternions, I'll show a bit of glimpse of that quaternion part also. But definitely group theory is also related, but I'll not cover in detail. So a finite dimensional space, vector space can be made if we have these numbers. These numbers can be real, these numbers can be complex. In our case, in quantum mechanics case or in quantum computing case, these numbers, in real numbers, are complex numbers. That means they have a real number or amplitude and a phase. Phase is also a real number, two real numbers. For each, there are two real numbers. But actually, if you imagine, I mean this x1, if you take two numbers, a two qubit thing, x1 and x2, apparently it seems that there are four real numbers involved. So degrees of freedom should be 4, right? One is the real part, one is the imaginary part of both the numbers, x1 and x2. So their degrees of freedom should be 4. But we'll shortly see, once we'll move to the block sphere, that actually the real degrees of freedom in this case is only 2. And we'll show how through manipulation of the state, how we can get that to that effect, right? That is the other information that you need. For a 2 qubit case, for a one single qubit case, the degrees of freedom is not 4 but 2. Okay. So every quantum state can be decomposed orthogonally in its component states. This phenomenon is called the Hilbert state decomposition. We'll see this in the last lecture today, how the Hilbert space, in general, what the Hilbert space is and how it is happening. But just for now, assume that every quantum state can be written as a part combination, sum of its parts, and those parts are its orthogonal projections. So we can write, say, I mean, this state, one qubit state is given here with the superposition of alpha naught and alpha 1. So we can write it in matrix form like this. This is the matrix form. And if I combine these two matrices, the magnitudes come here. So this is the column vector that I'm talking of. In this column vector, there are two complex numbers. This complex number top one, alpha naught and alpha 1. And similarly, if we measure the state, the single state, what happens is that either you get a zero state after measurement with some probability alpha naught here. That means the phase goes away. The phase means nothing for the measurement. Only the amplitude part gets squared, and that shows the probability either of 0 or the 1. The phase is not important in the measurement, but phase is very important once we perform the interferences. Once the entire path is generated, computational path is generated. So phases or the superposition or the covariance is important for that part. So phase is important there. Here, in the measurement, the only thing that we can see out of this thing is the probability distribution. And the probability distribution is for the 0 and 1. And after the measurement, definitely, since we have disturbed the system, now if we may have measured the 0, then we are in 0 state, and if we made 1, we are in the 1 state. So if we have more than 1 qubit, we can perform the tensor part. Remember, I mean, 2 column vectors together. So these are 2 column vectors stacked together. If I multiply these 2 like this, do a tensor part, then I can define the extra vectors, additional vectors, which are, I mean, 0, 0, 0, 1, 1, 0, and 0, 1. This is for the 2 qubit case. Similarly, if I go for the 3 qubits, this will generate how many possibilities, or how many orthogonal vectors will be there for the 3 qubit case, 3 qubit quantum state, 8, and so on. I mean, for every one, next qubit that you add in the tensor part, and you create a quantum register, the biggest quantum register, you multiply, you have the what do you say, the degrees of freedom increased by a power of 2, simply. So it looks very simple. I mean, I am getting enormous power, right? But this enormous power is not that enormous. Let's see how. Can you factor this? I mean, I've shown you a 4 qubit case. Can you factor it back to the state from which it got generated? Depends. In this case, you can, because it is alpha naught and beta naught. So if you separate them, you can have the 2 states. But it depends on the coefficients. If the 4 states have coefficients that you cannot separate, then you will not be able to separate them. This becomes interesting in 3 qubits and higher. How? In 3 qubit case, if we have I mean, all the degrees of freedom available, then we'll need 8 into 2 numbers. 2 degrees of freedom for every orthogonal vector. This is the 2 degrees of freedom. This is the 2 degree of freedom, right? So what we need is, what will happen is that we'll basically have the power of 8. But just in case, if we are able to decompose it back into the 3 qubit case, what happens? Actually, from the 8 complex numbers, you come back to the 6 complex numbers. If we are able to factor this state, this 3 qubit state, which is 8 dimensional, to 3 separate qubits, if you can show them in 3 independent qubits, then actually you are having only 6 numbers. And same is the case for the 4 qubit. For the 4 qubit, if we have a completely complete state, I mean, completely non-recoverable, non-factorable state, you will have the 16 possibilities. But if you can factor them, then how many numbers will lead instead of 16? How many degrees of freedom will be there? 8, 4 into 2. Because there are four different qubits, and each is having 2 numbers. So the actual power of the quantum computing comes once we cannot reduce this quantum state into separate factors. And this power comes from the entanglement. Unless you entangle, you cannot reach this stage. If you have simply stacked up the states, like you perform a Hadamard gate on all the qubits, single qubit, on any kind of single qubit rotation, not Hadamard necessarily, any kind of single qubit rotation, and you are not entangling them, you can always separate the states from that. So entanglement is not there. What entanglement does is, the real power of the quantum computer comes from the entanglement, as much entanglement as you generate. You do not necessarily, in every algorithm, you do not necessarily generate the maximum amount of entanglement. The maximum possible ceiling is 2 raised to power n. In no algorithm you reach 2 raised to power n. At least the known algorithm that we are talking of today. So that is the maximum possible that we can reach. That is the maximum possible parallelism that will. But it is reached depending on how much entanglement within the circuit you have created, how much interference you have created. That entanglement basically leads to physical interference, quantum mechanical interference. So unless you perform that entanglement, and the more you perform that entanglement, the more entangled the state is, the more is its power. But then maybe that state is useful or not, that is another thing. I mean, maybe a useful state needs less entanglement than you are. It's not necessary that you need to have, I mean, the maximum possible permissible state, and it does nothing. You want to have an interesting state. So normally the state that is generated at the end of your algorithm is having a mix of these 2 things. Some entanglement and rest is simple superposition. But superposition is essential to do the entanglement at the second stage. We'll see shortly. So one interesting case of the entanglement is 2 qubit case that everybody knows. It's called the Bell state. In Bell state, we reduce the 2 amplitudes completely to 0 by receptive interference, and let the other 2 amplitudes stay. This is one type of the entanglement. The other one is 1001 is entanglement, and then there are other possibilities also. There can be more for 2-qubit case. There can be more than one possible Bell state. There are other possibilities. Probably Dr. Madhya will cover. I hope so, because I mean, last workshop I gave him some I mean, at least I shared some slides with her. So I hope she's covering that tomorrow. So probably she will cover the Bell state in detail. But this is one Bell state I'm showing. What is happening here is that, say, if you measure this state, the first qubit, this is the first qubit, and this is the first qubit. Yeah, in the order, in the same order. So if you measure the Q0 state, and the Q0 state comes out to be 0, then the Q1 state is forced to be 0. It cannot be 1, because the possibility of it 0, 1 doesn't exist. Or does it? Similarly, if the second the qubit comes as 1, the first qubit comes as 1, the only other possibility is 1, 1. The other possibility 1, 0 has the 0 amplitude, so it doesn't exist. It will not show up in my image. So here you have perfectly created an entanglement which is giving you 2 possible states. This is a perfect case of entanglement for 2 qubits. You have completely eliminated 2. By destructive interference, you have completely eliminated 2 amplitudes, and that's what is desired. This state will be utilized again and again. I mean, once you will look for the higher order structures in your circuit, you will come across the Bell state at many places. You can even make a box and you can separate it in the entire circuit. Hadamard gates at the start, Hadamard gate at the end. You will see certain pattern in the quantum circuits with that you design. It's not that they come out of vacuum. You will see that Hadamard gates are applied at the initial stage. There is a purpose to that. You will see that the Hadamard gates are applied at the end also. You will see that the measurements are applied at the end. You will see that there will be this Bell states generated somewhere in between. If you combine or you make the boxes between the 2 states. So these are the primitives that we use in the quantum computation. These are the primitives, and based on these primitives, the higher order structures can be built. One example of the higher order structure is QFT, that probably will be taught to you in Shoralism. I hope so we can reach that stage. So what is happening is that the sum of the probabilities of the weights of the orthogonal basis is 1, first of all, and then in SO3 space, your operations of rotations which are happening on a block sphere, and they are exactly, since it is a reversible transformation or reversible operation, you can exactly reverse it by having a conjugated transpose matrix, which completely reverses the unitary matrix that you applied. Simply, I mean, you have a conjugate transpose of that unitary matrix, and it will be inverse of that matrix also. That is the definition of the unitary matrix. So all operations are unitary matrix, which are rotations, and additionally they are reversible. So why they are reversible? Because those rotations are unitary matrices, and simply having a complex conjugate of the unitary matrix generates creates a straight back, reverses the operation that you have done. These are just the definitions. I not, again cover. I have just shown you, how it is happening. So now coming to the thermodynamic entropy concept that, Dr. Detier yesterday, hinted upon. Once you perform a classical operation, which is irreversible, there is a minimum cost. You cannot go beyond that. We are almost reaching that minimum. He showed you a graph yesterday that we are almost reaching the limit, Boltzmann constant room temperature, or of the order of the Boltzmann constant room temperature. So switching operation, once it hits a limit, you cannot go, achieve a better efficiency than that. Right now, that is not the problem. We have not even hit the lowest ceiling, but the problem right now is heat extraction. But let's say we solve the heat extraction somehow. Then the main limitation is thermodynamic. The main limitation is the lowest ceiling of the switch. But and why this happens, this Boltzmann constant room temperature limit or thermodynamic comes into being, because these operations are not information theoretical. From information theoretic perspective, these operations are not reversible. You are losing information. Once you are losing information, you are increasing entropy. If you happen to revisit the Feynman lectures on computation, this is exactly from where he starts the quantum computing, from the reversible circuits and this thermodynamic limit. So it is interesting to go back and have a read on that also. So quantum gates do not regenerate the output. That means they are reversible, and they have to be reversible. Otherwise, I mean, they have to be a matrix first of all, and that matrix has to be reversible. So they should have same inputs and same number of outputs. That's the main limitation. And those matrices are unitary matrices. Since they do not destroy the information, that basic limit doesn't apply, because in quantum computers, quantum gates, you do not generate any heat. In fact, to the contrary, in fact, instead of generating heat, you have to keep it cool. This is completely reverse. You are spending energy, right? At the moment, we are spending energy, but that huge cost of energy, that cost of energy is only in keeping the system cooled, not extracting the heat from it. Opposite of what is happening in the classical computer. In the classical computer, you generate the heat, in fact, beyond the basic limit, a lot of heat. And unless you extract it, you cannot run it at its appropriate speed. Here, it is a complete reverse. Because it's reversible, it's a huge energy benefit. You are actually keeping it cool. So the disturbances of, external bath doesn't interfere with that supposition of coherence. And the other result is 1973, as the quantum information was, quantum computing came into being or emergence is somewhere around the Feynman proposal in 1982, but quantum information existed before that. So there's an original proposal by Charles Bennett, who showed that all quantum deterministic communications can be performed reversibly also. So there are reversible circuits, and reversible circuits are as good in heat dissipation sense, even if they are not quantum, if they are simply reversible. They are as good from the heat thermodynamic perspective as the classical circuits in terms of compute, but thermodynamically they are very much ahead. So this is the result that Charles Bennett shows quite, even before the emergence of quantum computing. In any quantum computing algorithm, these are the steps that happen. Just like I showed you an example of that analogy that you take the coins in your hand and then shake them and create a quantum state and then throw them. Then perform quantum operations that change the bytes and then throw them. That is a kind of analogy or a computational analogy. Here is the physics analogy or physics behind the quantum algorithm. What we simply do is, first of all, we select a problem to solve, which should be interesting enough. We should be commensurate with the power of the quantum computer. Then we design the Hamiltonian for that problem. We start with an initial state. That initial state encodes all the initial information we have. For example, if it's a molecule, we should have an initial estimate of the energies. If it is, say, some encryption breaking, we should have original estimate of the probable keys. If we do not have, then we generate a uniform distribution. We simply apply the Hadamard gate. Every amplitude is possible because we do not know which amplitude is okay. This is the simplest possible startup. But if we have the information about the original probability distribution, we encode at this stage in the state. Then we pick up the runtime and we apply the Hamiltonian for that time simply through a time-dependent Schrodinger equation. This is what exactly is happening. And for time-dependent Schrodinger equation, the equation is a unitary, which is this. So what we are doing is, based on this Hamiltonian, we are designing this exponential, which is again a matrix. A matrix exponential is also a matrix, and this matrix is U matrix, a unity matrix, which is getting multiplied by the your state. You perform it for time t, which is this time, and after time t, whatever the result is, whatever the final state is, you measure it with the measurement operator O, and whatever is your probability, it encodes your solution. Your measurement encodes your solution. This is the entire step. Entire quantum algorithm from the physics perspective. Now, how much time do we need for this thing to happen? That is the time scaling or the time needed for our algorithm. It should be polynomial. With the increase in the size, it should be polynomial, not exponential. There the advantage will come. And the second thing is how much resources quantum resources you need for the state itself and for implementing the gates or the Hamiltonian. These are the only concerns that we have from the algorithmic perspective once we design this algorithm. So now you have seen the computation or analogy from the computational perspective, information theoretic perspective, and from a physics perspective. Let's move ahead. So we have seen that the quantum operator U, if we have n qubits, then this quantum operator Q U in general, we apply on the entire register. So if we end-to-end encode this operator, full operator, then it will need 2 raised to power n cross 2 raised to power n entries. It's a huge matrix, by the way. Let's imagine n is 50. Imagine now 2 raised to power 50 into 2 raised to power 50 entries. Where to store it? Just imagine if for every entry you need 16-bit or 32-bit floating point number, real number. Just calculate the amount of memory that you need for the classical computer. Even for the quantum computer to implement this U directly like this is very difficult. You cannot directly implement it. What we do is we decompose this U, which is there, which came there from the Hamiltonian. We decompose this U. By the way, don't get disappointed, because most of you are for the physics students, for those who are not from the engineering background, don't get intimidated by the terminologies. These are physics terminologies, but we are not talking physics here. This Hamiltonian is just basically a matrix. This U is basically just a matrix which is encoding your problem, nothing else. The name comes from the Hamiltonian, and the name comes from the physics, quantum mechanics, nothing else. Rest is your domain. In fact, for your domain, you can design this U better than any other physics student. While they may be more comfortable with this terminology, you might be more comfortable with your domain expertise to implement this. And that is what is needed. If you want to solve use cases in the quantum computing, we need to have people who can design this U. And how to design this U? To directly implement this U, even in quantum computing, is a huge task. Instead of that, we break them into steps. That is what the algorithm does. Any algorithm, even quantum computing algorithm or quantum algorithm, breaks the main task, the full task, into steps. And those steps are the gates. And this is called quantum logic synthesis or transpilation. Transpilation is a bit extra because you do the transformation also. It is compilation plus translation. So this is the compilation part in that. Just imagine this is the compilation part that we have discovered. So this is the first gate. This has been discussed at length, but I just want to emphasize that for the 1 qubit case, which has the 2 degrees of freedom, 2 raised to power 2 is 4. So this is a 2 cross 2 gate, right? For 2 degrees of freedom, this is a 2 cross. A single qubit is a 2 cross 2 gate, and this is something extra, which is the amplitude thing that basically gets that basically distributes the state across these 2 orthogonal components. And interestingly enough, if you apply this gate, Hadamard gate, on 0 state, it gives you an equal superposition of 0 and 1. If you apply it on 1, it gives you an equal superposition, but with this plus sign replaced by minus. That means there is a phase reversal or phase change. But in both the cases, if you apply the Hadamard gate again, whatever is there, if you apply Hadamard gate, whatever state is there, if you apply Hadamard gate, then apply Hadamard gate, you get the state back. So Hadamard gate in this case as a unitary is shown inverse, and you can try this also. You have to transpose it. Conjugate transpose is conjugation does not need any change except this. I think 1 minus 1. So rest of thing is just you have to change the place. Everything is 1, so it becomes its own reverse also. The important gate which creates entanglement, as you talked, that entanglement is very necessary, is a C0 gate. This is the first gate that basically entangles the 2 qubits. It creates that conditional, like there is a if then else statement in the computers, right? If I have the if then else statement, I can write a loop also. Can I? Anybody who has the reservation on that? If I do not have a loop, for loop, I only have a if then else statement. Can I write a loop? If compare something, then continue something, and break only when the condition is not met. Loop is there. So if then statement or a conditional statement can do anything in the classical computing also. Here also, once this thing comes in, now you can perform any kind of computation. Without this, there is no computation possible. You can create interesting states, you can measure them, there are probability distributions, but you do not compute. You start computing once you have this entanglement. And this is the very first example of an entanglement gate. This entanglement gate, basically, what it does has been explained a lot, so I'll just skip it. Just briefly, you can see these 0 and 1 which are red. You can see that once the control qubit is 1, then it flips the target qubit, which is Q0. In the red cases, you can see. If it is 0, then it does nothing. This is an even more interesting gate because this gate is universal in the reversible computing. If in reversible, not quantum computing, reversible computing. If in reversible computing, I have only this gate, this is as good as having a NAND or NOR gate in non-reversible case. So it's all the kind of a quantum logic because it's also a conditional gate. So all the kind of computation in reversible sense can be implemented by having a Toffoli gate or control not gates. When both the two controls are 1, only then this bit flips. Exclusive OR. Okay, but for quantum computing, apart from Toffoli or C0, we also need Hadamard and one more gate, right? Rotation gate. So apart from this, we need gates. For quantum computing, this alone is not enough. There is a complete set, fundamental set that we need. Just like in classical, we need a set also. Sometimes we define the classical universal set as not and or, right? So in this case also there is a set, universal set that we need. And once you have the universal set, you can implement or design any quantum algorithm. But how that quantum algorithm will get transpiled onto the quantum hardware is a completely different story that we'll cover tomorrow. Because they have optimized their circuits for certain entanglement gates and certain rotation gates. Whatever you do, they will first transform those gates into their own language, a separate gate set language, and then it will get implemented. And that is where somebody, I think Dr. Razak told the thing that the results are not coming okay. The results are not coming okay, but at times our translation, because we are not checking translation. We are not checking translation, cross-checking translation. So at times what is being transpiled and going to the quantum computer is not what we intended to send. Because these transpilation compilers are at a very early stage right now. And moreover, there are other constraints also. I'll not go into detail, like topology constraints. But whatever is, important is that we start with some probability distribution. We create this probability distribution normally with the Hadamard. This you likely see in all the quantum algorithms. What these Hadamards are doing is generating equal probability or uniform probability distribution. That means we do not know which outcome is probable. But if we know which outcome is probable, we can encode that thing here using rotation gates. That happens in the quantum machine learning. In quantum machine learning, we exactly encode the data. Here, since we do not know which state is probable, so we have just initialized the state as a uniform probability distribution. Then we apply certain entanglement gates which are there. This is just an arbitrary circuit. This is doing nothing. I've just run the circuit, how the circuit looks like. And then there are certain rotation gates. These are the swap gates. Swap gates are doing nothing but swapping this qubit with this qubit. This qubit with this qubit. Just reversing the order in the order of the things. And then finally, whatever is coming out, whatever probability distribution is coming out, we measure it, and once we measure it, then we get the stochastic result that we discussed. Our output or measurement is a probabilistic output. It shows how much the two vectors, how much our main state is having a projection on some orthogonal basis. To choose that orthogonal basis, we are at liberty. We can choose that orthogonal basis as per our liking. We are not constrained that should always be 0 or 1 for every qubit. We can choose as a measurement qubits, measurement state, measurement frame of reference, we can choose plus and minus also, or some other state. Anything that is orthogonal on that sphere, we can choose for the measurement. But what measurement is doing, it is by a dot product, it is giving us the projection of our state, which is encoding the probabilities on that particular orthogonal basis. And one consequence of the measurement is that if you do the measurement, then everything changes back to the state in which you have measured, right? So one consequence is unless you measure, you cannot reconstruct a state. So if you measure, the state is destroyed. Simple cloning, no cloning theorem simply comes from this measurement philosophy or the measurement constraint. Now the question, answer might be wrong, right? You may have designed a very good, circuit which has almost reduced the possibilities of say wrong answers to zero, near zero. But still, it's a random thing, so it is possible that you get the wrong answer. But a good algorithm is where you have reduced those possibilities by destructive interference so much that it is very highly probable that you get the right answer in few throws. And you can always counter check. After each throw, whatever you get, counter check it via inverse algorithm on a classical computer. And you will find if you get the answer in few tries or not. But the problem occurs when there is a wrong answer due to these phenomena, and you say, I say that this state, I say that this is my one circuit, and then this is feeding this other circuit, and then this is feeding third circuit. So if there's some error here, and it gets fitted here, and it gets simplified here, and it further gets fitted here, it gets simplified here. So unless we have some kind of a error mitigation or error correction thing, the error by the time, since we are dealing with the erroneous gates and the erroneous initialization and the decohering states which are rapidly losing their coherence, so the errors get amplified. So the deeper the circuit is, the more is the possibility for the error to build up. But I'll show you an interesting case how we can avoid that in the next lecture. There is you can always go shallow. This is deep, having more depth, but you can always trade off the depth for width. How? We'll see shortly. And this is the outcome that we have seen before also. So in summary, what you are creating is a superposed state in the Hilbert domain, which is superposition. In composite systems, you are creating the composite state using the tensor product that we have seen. And then, if unless we introduce the correlations or entanglement, we cannot have the maximum path of our representation. So our representation is fully utilized, or it gives us a maximum leverage in the computation as much as it is entangled. And lastly, the measurement rule. Measurement rule is, by the way, a Hermitian operator. It is also matrix, but I'll not go into detail. It is different from the unity matrix that we have discussed. What are the application areas? These are the application areas which are currently being used. So I'm not talking of something that is not being used. It is what is being utilized. The quantum computers are being utilized right now with the NISQ era. In the NISQ era, these are actually being utilized. You can have claims and counterclaim, how good or bad they are, but in all these fields, they are getting utilized, which I mentioned. And while quantum computers are very good in certain things, and they are performing very well, and probably they are the right tool, at the same time, the people from the classical domain, or even sometimes teenagers, 18, 20 years guys, they are coming up with the classical algorithms that beat the quantum advantage somebody has shown using quantum algorithm. So this is happening almost monthly now. Last year somebody did it. This year somebody did it. So this is happening. The classical is there to beat it. Because we have not discovered all the classical algorithms, or have we? We have not discovered all the classical algorithms. With the AI, our discovery rate will increase, because previously we used to hand code or hand design the algorithms. Now we are trying to assemble the models using the data, lot of data and large models. So maybe we have a classical case which beats a comparable quantum case and shows that its advantage is better. So it is fighting back. But definitely we know that for certain time to come, for certain kind of problems, quantum computers will be better than the supercomputers. That is for sure. This is my conclusion. There is a technological promise of the quantum computers, and last 5 years have shown great progress in that. The research in the quantum computing, because you all are researchers, probably you have come up, you have came to the workshop with the aim of continuing your research. So it is a high risk research, but with a high payoff. Imagine in Pakistan, you have to find the people who can teach you quantum computing. And this is not only in Pakistan. I've come from Germany. I can assure you, even there, At least in my department, I was in Artificial Intelligence Central Institute of Germany. There was nobody except one person who was Russian and who is now spearhead a separate department separately at Max Planck. So maybe in a community of say 500 people or on 5 floors, just 2 people in one artificial intelligence department. So imagine how much rare this thing is. So if you are there and you have hit the bull at the right time, this high risk has paid off for you. It's a high payoff game. But the problem is we do not have programmers. In fact, our programmers at the moment are weaker than their hardware experts. Frankly speaking, I would say, very frankly, that hardware experts are better and physicists are better at the moment than doing many things in the hardware compared to the use cases. But the problem is physicists can come up with a very good hardware, but what is the use if it doesn't solve something for somebody? So what is needed at the moment is this is the time for the takeoff. And where the takeoff occurs, there physics goes in the background and then the engineers come in the front because these are the engineers who apply the technology to the use cases. So what we need is a lot of engineers now. Unfortunately, Pakistan, as far as I know, I think so, in the community I know, I probably am the only engineer, sir, with the background, hardware and software, at least in the Islamat Pindi. There are physicists people, there are mathematicians, quantum optics people, but there are very few engineers and we want more engineers in this domain. Any question? And then we start the Hilbert phase. No question?
Can you explain the part where you say that entanglement gives us computational power? It reduces the number of coefficients, but how is that beneficial? How does that increase?
You see, if you have 2 raised to power n, you do not, for example, for a 3 qubit case, if you do not have 8 numbers, 8 degrees of freedom, and instead you are getting only 6 degrees of freedom after decomposition, whether your power of representation has reduced or increased. For 16 qubit case, 4 qubit case, if you are instead of 16, you are getting 8 possible weights. Your power of representation has decreased or increased.
Power of representation has decreased.
Because you can factor. But once you create the entanglement, even partly you create entanglement, few qubits cannot be different, cannot be shown separate. I'll show it in the next slide on the Hilbert sphere also. In that case, you cannot individually show the states on the Hilbert sphere, on the individual Hilbert spheres, on the individual qubits. You can show the combined state or entangled state in a hypersphere, in a hyper block sphere, but not on a regular 3-dimensional sphere that you are seeing. So your power basically comes after entanglement once you cannot factor out the states. Because if you can factor out the states from the tensor product, then probably you are having lesser degrees of freedom than maximum possible, as I showed. Any other question?
Answer: quantum gates are reversible through mathematics here, all that. But if we talk about physics, so behind why they are reversible is that either they produce heat or we control them. Is that way or something else?
This is one thing. The main thing is whatever operation you are doing, in the physics domain, unless you perform a measurement, because they should not measure anything. The only irreversibility in the physics comes from the measurement. So our measurement operator should be 100% irreversible. Correct? So if some operator is partly doing the part of measurement, which it can do, by the way, there can be mixed operators. Let's not forget it. We are talking quantum computing here, but we are not talking quantum mechanics. In quantum mechanics, there can be possibilities where 2 things are done through one operator. It is possible, mixed operators. So the problem is that, if you are not performing measurement, then whatever is remaining has to be reversible because it's a matrix. And the thermodynamic advantage is a separate thing. That is also there, but this is the mathematical answer that I gave you. Any other question? Any question from the online audience? Okay. I'm sorry. Somebody, Ms. Fatma has told me to speak slowly, which is basically my main limitation. Unfortunately, I cannot help it. So I'm sorry on that account. I try to keep this thing in mind and maybe try to speak, but then we'll cover less things. If I start speaking slowly, then there is so much to cover that probably I'll not be able to cover the slides that I've made. Okay, any other question or suggestion? I have many questions. So Nurul, if you have many questions, you are always welcome on the next days, or you can come down to the quantum computing lab NUST also, and there is a group also you can join, and you can always throw your question in on the group quantum computing QCL NUST WhatsApp group. Okay, there are 786 members right now. I mean, it's a great achievement. I have not seen a workshop. I mean, I hope it is correct on number. This is in my life. This is the widest attended workshop. 786 members. If they are actually attending, I'm not sure. Any other question? I think so. Previous remarks. Any previous remarks? Nothing. So there are no questions from the online. There are no questions from the audience. We move to the last module. Okay. सर एक भाई ब्रेक करें जब इमुलेशन से मैडम की मरियम आप इनके काम से पहले हम ब्रेक दे देंगे आई होप यू डोंट माइंड अगर आप ब्रेक आपसे पहले दीजिए चले when we entangle two qubits we have 4 dimensions then every single dimension will be a bit yes every single dimension will be a combination of 2 bits not a bit because there are 4 orthogonal vectors. Each orthogonal vector is being represented or encoded by 2 bits. So every single dimension will be 2 bits. If it is measured, it will give you 2 bits. So now let's come to the Hilbert sphere. And let's, this will be right. I think this will be most interesting part. I hope I can keep the audience with me in this because I'll be connecting the Hilbert space across the domains now. Not only quantum computing, we'll start from almost signal processing to quantum computing to machine learning. So this will be probably interesting because what I love to teach is this part. Rest is, many people can teach you and can maybe teach you better than, but this is the part that I am expert in. So this is my most favorite part. I hope I can keep the audience with me in this, please. So this is Hilbert space, as simple as it is. It is a vector space. It can have any number of vectors in it. A Hilbert space is simply a vector space which defines a dot or inner product. And by this analogy, we can define many kind of spaces as a vector spaces. We'll shortly see. So this to show you just one example, which is a very basic example, which are actually the vectors that you see every day. In these vectors, you have these are 2-dimensional vectors in a 2D space. So there are 2 numbers representing each vector, just like the qubit, but these are real numbers. Let's assume that it is a complex space. So these are 2 complex numbers. Just this. Let's assume it like this. So these 2 complex numbers. These 2 complex numbers. Or let's say for the timing to keep it easy, let's keep them real numbers. These are 2 real numbers. What the dot product does is it doesn't give us distance. I have not talked of distance. Once I add a distance to a Hilbert space, it becomes a metric space. And if I remove everything, it becomes a topological space. If people have a bit of understanding of the math, if everything is removed, only structure remains, the order remains, it is a topological space. If I add an inner product, it becomes a Hilbert space with a vector in the vector space. And if I add a distance measuring thing, some kind of a distance matrix, it becomes a metric space. Right now, I'm not talking of the metric space because I don't need metric spaces. In AI, I need. As far as this space is concerned, this is not a metric space. These are simply vectors. And what the dot product does is dot product basically gives you the projection of one vector on the other vector. This dot product gives you projection of this vector on this or this vector on this. Both the same things. They're equal. And it can be easily created by multiplying the two vectors, keeping the orientation, not the order but the orientation. One should be the row vector and then the second should be the column vector. This can be easy. And this is very important because this directly converts to the classical kernels which are used in the machine learning. And in classical kernels also, you basically by projection, what you are trying to get is the similarity of this vector with this vector. So exactly if you have a kernel and you have two functions, you are with the dot product, you get the similarity in that kernel. You get with the two functions, you get by the dot product, you get a similarity. And if you have many kernels, which can happen, we'll shortly see how it can exponentially explode. The kernel can exponentially explode. Then probably the quantum advantage can come, where they become classically intractable. Just this remark, and then we move ahead. Just for the time being, note this remark. I'll come back to it shortly. But remember that what is the Hilbert space. Now this is also a Hilbert space. In this case, the vectors are functions. This is one vector, and this is another vector. I want to check the similarity of these two things. I define this integral, which is a dot product. The important thing to note is that this dot product only happens from certain data range to certain data range. It is not universal. Although in this case it can be universal, minus infinity to infinity, but in general these numbers are fixed. Particularly once we are performing the AI, these numbers depend on our minimum data limit and maximum data limits. And our projections or similarities are only true in that data range. Beyond that, we do not know. We are uncertain. So this is one function. This is another function. This is one vector. Assume this is one vector. This is another vector. If I define this integral, this multiplication, this is doing exactly the same thing. It's multiplying at every step. It is multiplying this thing with this thing, and then integrating it. Just like a vector multiplied by a row vector multiplied by a column vector, and then everything summing up at every point, right? This is what happens in the row by vector by column vector. You multiply at every step, and then you sum up. That is a discretized version. Here you are seeing a continuous version. Every step multiplied by every other step, and integrating or summing. So this is a dot product. Interestingly enough, this case that I showed you, these two vectors that I showed you are also orthogonal. How they are orthogonal? Let's find out. If I multiply them in the range -1 to 1, which I've done here, one is the function pi pi, and other is with the frequency 3 pi, I think so, 2 pi and 5 pi. So if I multiply these, and this is a multiplication, there are certain positive parts and certain negative parts. If I add positive parts and negative parts, they exactly cancel out. So these two functions, which I am saying that they are vectors in some sense, in some analogous sense, are also orthogonal. And this is exactly what we do in mathematics. We have invented a complete domain of transforms in signal processing using this orthogonality concept and Hilbert space, starting from the Taylor series. People normally undermine it, but that is also on a power series. That is a kind of a power series where we have this kind of orthogonal terms. Fourier series is more common, but the example I've shown you is a Fourier series. These are two Fourier orthogonal bases that I showed you, and once I multiply them, I try to correlate them, the answer is 0. That means these two bases are orthogonal. In some function space, which is a Hilbert space or a vector space with this dot product, these two functions are orthogonal. There are more than these functions. In fact, every integer multiple is orthogonal. If you try every integer multiple, but there are infinite number of bases in this case. There are a discrete but infinite number of bases in this Hilbert space, which we use for signal processing. So if we can have this infinite bases, and then we can combine the projections on these. For example, in this case, there are this is a two-dimensional case, so there are two possible orthogonal vectors. This is one possibility. I can rotate it also. This one can also be orthogonal vector. This one can also be orthogonal vector. This one can also be orthogonal vector. So I can rotate this orthogonal frame anyway, and they will still define some separate set of bases, and we can, any state or any function that we want to decompose, we can decompose in these orthogonal functions or orthogonal basis functions. Any function which is there, we do not know what this function is. We actually want to find it out. Either we know it or we want to construct it. Either if the function is known, we want to analyze it, decompose it. If it is not known, we want to construct it. And this thing can be done by using these basis functions. These basis functions. Now, it is not necessary that I have the orthogonal basis function. I can have a bi-orthogonal set also. That can also does the same thing. But the only difficulty in this case is, this happens in the AI, by the way. The difficulty in this case is that some information of this state is of this basis vector is there in this basis vector, and some information of this basis vector comes in this basis vector. This is the main difficulty. So the states get mixed up. Here it is not like that. If there is some component which is on this basis vector, it is completely independent of the component on this basis vector. But we can have bi-orthogonal or orthogonal bases also, and they can equally be used for the composition or the decomposition of the functions, but with a caveat that each basis vector will carry the residual from the other. So we can create this kind of a measurement. We can create this kind of a measurement, orthogonal measurement in block space. We can also create this kind of a non-orthogonal measurement in block space. Though we rarely do it, but it is possible. And we should only have the vectors as many degrees of freedom we want to analyze. In this case, it's a two-dimensional space. So any vector in this space, which is lying in this space, can have at best 2 degrees of freedom. I do not need more than 2 vectors. In fact, if I create more than 2 vectors, the third vector is unnecessary. It can always be reconstructed by the other 2 vectors, because there is no linear independence. One vector, additional vector, is linearly dependent on the other. It can always be created by those 2. So the span of this base, this 2-dimensional space it is not a Euclidean space, by the way. I have not defined any measure or matrix or distance here. So this space is a vector space, and this is a 2-dimensional, 2 degrees of freedom vector space, just like a qubit. What can happen is, in most of the cases, especially in signal processing and even in the quantum computing, what can happen is that sometimes exactly this happens in the Grover algorithm. You'll shortly see the Grover algorithm. Exactly the same thing is happening. Once you'll see that this thing is happening there. You can always choose a subspace which contains your desired information. Normally, we do it once the desired information is there in the subspace, or once the subspace contains the most information and the remaining space, we consider it as orthogonal to the rest of the space, and we discard the components there because the projections there are almost meaningless. Here I am showing you a discrete case, but it can be an infinite dimensional Hilbert space also, like I showed you in case of the Fourier series. In Fourier series, the bases were infinite, minus infinity to infinity. All possible discrete values of 1 pi, 2 pi, 3 pi, 4 pi, I showed you, right? And other ones also, n pi. But actually number of bases were infinite, despite discreteness. So here, I am not showing the entire basis, but you can always choose a subspace which contains your desired information or most information and discard the rest of the subspace. In this case, if I want to discard some bases, which bases will I discard? In this particular case, which subspace will I discard? Anybody? Answer? Mushkil nahi hai. Not difficult. Okay, if it's too difficult, then I answer. No. If this is our vector, and this is our space. This is a three-dimensional vector, 3 degrees of freedom vector. So we have a 3-dimensional base. Now, tell me, there is a subspace shown here. This is a subspace. Tell me which subspace you can discard in this case if you want to keep the maximum information. Okay. which you can see, which thing you can't see? Left one, and you want to discard this? Anybody else whose answer agree? I think to keep maximum information, I'll discard these two. I'll discard this subspace and I'll just keep this basis vector because it is getting the maximum information. This is getting the maximum projection. Projection. This is the maximum projection. Similarity between the vectors. This is one vector, and this is composed of three vectors. So it's the similarity of this vector is greatest with this vector, this basis vector. So I'll keep the magnitude or the part or decomposition on this vector. I can easily discard this subspace. In fact, this is not exactly the kind of a thing that is done. Normally, this subspace which is discarded has a very minimal component. Here, it still shows a certain substantial component. But normally, what we do is that the space we discard is having a very minute component, and rest of the subspace, which are multiple vectors, not a single vector, is having the maximum possible information. And this we regularly do once we do the information compression. In information compression, like DCT, like other transforms, we regularly do this kind of compression. We transform a signal to a Fourier space or a cosine space and keep those components, those basis vectors which have maximum information, discard rest, and there will be very less loss. Your JPEG, your PNG works exactly like that, which compresses you from say megabytes of picture to just kilobytes. Doing this process, the subspace discard, and this happens not just in image processing, not just in signal processing. It happens in CFDs. Dr. Imran can tell you better. These features are basis vector here. I'll shortly show. Okay. So if I want to reconstruct, what is the best possible reconstruction that I can get? If I have infinite number of basis vectors, like happens in the continuous case, like in Fourier series, the more components I add, the more better approximation I'll have. Here I have only added 10 components, first 10 basis vectors. I have lost some information, and that loss is appearing as this basically this is a pulse. But as you can see, there is a ringing effect here also. This is a ringing effect here also. So this is a loss of information or residual that is existing. But still, I can fairly see and I can fairly appreciate that this is a pulse for many applications. So n is equal to 10 maybe might be good enough for me. It is up to me. If I increase this n to 150, I'll get even better approximation and so on. So the more I increase the width or the summation terms, the more accurate the result is, the reconstruction is. Now let's connect it to the entire thing we have done to the digital world. What we do in the digital world is that we have a continuous case. Say sinusoid maybe. We discretize this sinusoid on the time domain, and then we also quantize it or digitize it along the vertical axis. And after these steps, whatever digitization occurs, this step, we change into binary words. This is the entire process of doing the digitization. And using these binary words, then we perform the digital communication. This discrete information, which is a binary word, a finite number of symbols, we perform the computation one step at a time, and that's how the digital computer works on a real world data, right? That we have seen. And in the real world, it is an infinite dimensional space, but we can reduce by discretization. We reduce it to symbols, and then we utilize them. Now, what happens is, as soon as now after discretization, I can implement the thing in the discrete mathematics. Now the functions have a discrete numbers. Because I've discretized and I've changed to binary and Boolean logic, now the numbers have a discrete. Numbers have discrete values. Like you can see in this Boolean. In this truth table. This is a truth table for the half adder, for which the circuit is shown here. But let's just focus on the truth table. In the truth table, how the circuit is implemented, we have just chosen the terms where the output is 1. And wherever the output is 1, we have implemented those inputs as a basis. This one and this one. In fact, this is a circuit. These two bases with amplitude of 1 are getting summed up with this OR. These two basis vector with amplitude of 1 here are getting summed up and giving you this function, some function. But if you look closely, there are other basis vector also, but they are present here. These basis vectors, these 0 basis vectors are now present here with the 0 amplitude. So you see the summation, the Hilbert space, and the basis vectors here. In fact, every basis vector here is orthogonal to every other basis vector. And just like the inputs and the outputs are 1, similarly in the Boolean case, the weights of your summation or Hilbert space is also 1. It cannot be, unlike quantum, it cannot be some number, some analog number. It has to be either 0 or 1. This is the main difference between a detail and log. Understood till this point? Hilbert space connection to the detail word. Now let's go a bit further. Another important thing which is common in both the analog and the digital domains, because I mean this thing has a name in the neural networks or AI. It is called the universal approximation theorem. You actually need only 2 layers of operations to perform any function, whether it is analog or it is digital. Analog case, you can construct any function by a transform, a sum of the basis vectors with different weights, analog weights. Digital case, basis vectors multiplied by 0 or 1 weights, and you can reconstruct in 2 steps. The first step gives you the basis vectors, and the second step simply sums them up, while the weights are 0 or 1. And you can design any function, any possible function. I mean, there is no escape from this reality. The only limitation with this approach is if the truth table, which I showed here, it grows in number of terms or inputs or state plus input. The truth table will be state plus input. How many words you need for the state, how many words you need for the inputs. So if the only thing is if it grows, the circuit itself in terms of bits explodes in digital domain. But in just the shallowest possible terms, you can have all the AND gates implement the ones in the truth table and then simply OR them and get the particular Boolean function you want to define. The other difference is how many Boolean functions are actually possible. Let's say just in the case of the 2 inputs, there are 16 possible Boolean functions which are shown in this table. Some of these are trivial functions. For example, I mean this and ones are totally trivial. You have not even seen them, these ones. You have not even seen, I mean, there's some this function also, this function or this function or this function or this function, because there are certain limitations. We only use normally AND out of these, OR out of these, NOR, NAND, NOT. These are the functions we commonly use. Just you have not seen, but these are possible. So just in with 2 bits, 2 input bits, the number of possible functions is exponential, but it is still finite. Unfortunately, in quantum computing case, it is not like that, because the weights are not 0 and 1, they are analog, so you can have infinite possible functions, just like the neural networks or AI case. Understood? आगे चलें? Any question till now?
Had not been this era, the analog, we would have used Fourier transforms instead of SPD. So we would have used a continuous function with multiple multiple AND gates at the same time.
In fact, we always change a continuous function, we discretize it, and we solve it in this digital domain. That's what we do. Even for the neural network, if we see the implementation at the GPU level itself, the hardware level itself, these are the Boolean functions that are happening there, or they are acting. You discretize your main function, analog function, and then you implement the digital case. But digital case explodes very soon because of 2 raised to power n possibility that you have seen here. Okay? Any other question? Let's move. Now coming to the Hilbert space, which is the block sphere, which is a Hilbert sphere for the Hilbert space visualization for the qubits, a single qubit. What I am showing here is a Hilbert Hilbert space visualization for a single qubit, and it's called a block sphere. So this is your superposition, and in general, I need 2 numbers here and 2 numbers here. So for a single qubit, I'll need 4 real numbers. In general, I should need 4 real numbers, but this is not like that. Actually, what happens is that I can rewrite this thing like this, because there is a hidden constraint that you don't see here. What is that hidden constraint? Alpha naught square plus alpha 1 square is always 1. So what I can do is I can take the phase part separate, and whatever is remaining, since cos theta square plus sin theta square is 1, so I can define or parameterize that part with single number theta. The remaining phase is here also and here also. But I take the phase from here, I take it out, and then I negate the phase, whatever I taken out. Since it is a multiplication, so I implement the invert phase and then just add it here. So this phase is now out, and inside you see there are only 2 parameters, theta and phi. These theta and phi, this phi is basically a relative parameterization between the 1 basis vector and the 0 basis vector, while theta is basically that amplitude part. So I can encode 2 numbers in this qubit. In fact, I can, and this is the part outside is the global phase. Normally it is left, generally it is taught, or it is thought, it is just practice that we leave this phase part out, just the global phase part out. We say that this doesn't matter, we are just concerned about the relative phase, which is parameterized by phi, and the constraint on the amplitudes, which is parameterized by a single number theta. So actually the 4 degrees of freedom have now converted to 2 degrees of freedom, and these 2 degrees of freedom are now implemented as theta and phi on this block sphere. But the problem is the visualization of the orthogonality. On this block sphere, the orthogonality is not in the regular sense as you define, in the Euclidean sense. What you see is that the orthogonality is a kind of a parallel or 180 degrees opposite vector. If this is 0, then its orthogonal vector is 180 degrees opposite, in fact. But actually it is 90 degrees opposite in the block sphere visualization sense. And this is 1. Similarly, if this is positive Bell state, then this is negative Bell state. So not Bell state. If this is the positive vector, then this is the negative vector. In fact, you can define any orthogonal basis state like this one, like this one, like this one, like this one. Any side, make a clean cut, and it's a orthogonal basis. And you can measure in any orthogonal basis. We normally measure in plus minus or 0 and 1, but there are other possibilities. You rotate the frame and measure. The state is there. The state sits over there. How you decompose it and how you measure it is up to you. And it is one major feature or one strong feature of the algorithms, quantum algorithms. In many quantum algorithms, we use the canonical basis, but finally end up measuring in plus and minuses. It's a strength. Measurement itself is strength. Okay. So just rotate the reference frame and you will have the new measurement basis. Okay, just go back. Now, where is this global phase? Anybody can, in this representation, anybody can tell me where is this global phase? The global phase, remember, the global phase does not decompose on the orthogonal vectors. It doesn't show up as a measurement. where it can be incorporated in this visualization. कैसे? ठीक है, समझ, okay, good, one answer, partial answer. अभी boundary बताओ, I mean, if you place something, I mean, if it changes the locus, it will create some disturbance in the orthogonality, orthogonal projections. So how to encode it? Okay, this is my, let's say, this is me, this is your vector, and it can be anywhere in the sphere. This is the locus of the sphere. My arm is unit length and it is fixed. I can have a locus of sphere, right? Where to encode the global phase in this physical sense.
Whole sphere rotates. Locus also rotates.
Good. So this is, can I do this? If I do this motion, which is a locus rotation around its own axis, rotation around its own axis, not rotation in the swing sense, but rotation around its own axis. If this is my rotation axis itself, and I rotate like this rotation will not reflect on any of the basis vectors. So the global phase lies over here in this rotation. Is it, in general sense, it is not beneficial. Can we somehow use it? This is an abstract, a very small abstract from my PhD thesis, where I worked on the biomechanics. And this is the part is from a famous paper that got published first as a conference paper and then as a journal paper. It got the best paper award in Japan. We introduced a concept that we can, any SO3 space can be transformed into 3 components or lesser components. We transformed into 2 components. Swing, which has 2 degrees of freedom, and a twist. Swing, which is 2 degrees of freedom, and a twist, which you can see. Since we can represent the SO3 spaces in the quaternions also, so from quaternions, which have extra degrees of freedom, by the way, because they are constrained, we can actually derive these 2 swing and twist states. The details is there in the paper, and basically, if you want to encode, this is one possibility to encode the information. If you encode that information, if somehow you can apply a gate which encode the information in the global phase, then the gates can be created, specialized gates can be created that can extract that information also, and even use that information for entanglement and all the processing. Understood? Normally, this general phase is global phase is discarded because normal algorithms do not treat it as but it is there in the industry. Remember, it is there in the quantum state. It is not absent. Now I'll just wrap up generally, madam. I hope I'm not exceeding your time. Abhi kya time? Okay. So I'll just now a bit of hurry up. I'll connect this thing now with the AI. That will be interesting part. So entanglement you have seen. Oh, just one point. Like I was saying, I think Farzan answer. You questioned that how why this is the same answer to your question. Why if I cannot decompose, this is a computational space or a Hilbert space of 3 qubits which have 8 components. Hilbert space of this is a computational space. This is not a qubit space. This is a computational space. Computational space has 8 components. So these are the 8 components. If I cannot write them separately as 3 qubits, I cannot show them as separately as 3 qubits, then they are entangled. And maybe sometimes I can partly decompose it, partly factor it and show 1 qubit separate and rest of the qubits still remain entangled. So then I cannot show these 2 spheres separately. But what I can do is that whatever is the entanglement, say all 3 qubits are totally entangled, or this, let's say this qubit factoring gives us some part which gives us this qubit, but these 2 qubits remain entangled. What I can do is I can define a hypersphere in a higher dimension where I can still show the state, but not individually on these spheres. Because if I can show something individually on these spheres, then the degrees of freedom certainly decrease from 2 raised to power 2 raised to 3 in this case to simply 6. This is what the entanglement does for us.
They're not entangled then.
If I can decompose a tensor product into factors, separate factors, and those separate factors are relevant to a qubit, then I can have the individual qubits. If I cannot disentangle them, or I cannot decompose them into that tensor product cannot be decomposed into individual qubits, then it is entangled. It can be partly entangled also. Like I said, I can factor maybe one qubit, which will give me the visualization here, but these 2 qubits remain entangled. In that case, if these qubits remain entangled, I cannot show them on two block spheres. I need to design a hypersphere for that. If I use a higher dimensional visualization, I can show the entangled state. I am telling from the perspective of the visualization. If you want to visualize every qubit, it is possible only if they are not entangled. If they're entangled or partly entangled, then the part which is entangled cannot be seen in the regular Hilbert sphere, the regular block sphere. There can be a block sphere made in a high dimension in which that entangled part can be shown. But we can visualize it here on the slide. Okay? Any question? And these are the rotations that take place. Remember, I talked about SO3 space. SO3 space, any rotation on this Hilbert sphere, any rotation on this Hilbert sphere, this is a general arbitrary rotation. It can be in SO3 components can be decomposed, and there can be, this is one rotation, this is one decomposition, ZXZ. There is ZXY, there is XYZ. There are multitude of decompositions which are possible. 3 number decompositions which are possible. This is just one kind of a decomposition that I am carrying out. So any arbitrary state can be decomposed into 3 separate rotations and then applied. This is exactly what happens at the time of the transpilation. So what is happening in this case is that the entanglement and the interference is being created in this part. This part is creating the computational paths where the interference is occurring. And as the interference occurs, it basically constructively interferes certain amplitudes and destructively interferes the rest. And once we measure, the constructively interfering amplitude is shown. Rest are destructively interfered. Now connecting it to the AI. In AI, we also have a basis vectors. Because in AI, what we do is we want to learn a function which we do not know, but we have the data for it, right? This is a problem. We have a lot of data and we think some function represents it, or some function can fit in it, because it is doing some task. This data is coming from some task, actual task. So probably there is some function, some pattern is behind it, and we want to find or fit that pattern. So what we do is we invent our own basis vectors. In normal machine learning, we invent our own, manufacture, handcraft our own basis vectors, and then try to find the similarity using that same integral with those basis functions. For example, in this case, I want to find the similarity between these 2 functions. Maybe this one is the basis vector, this square pulse is basis vector, and this is the function that I want to see how much similar this function is to this. So I'll either perform convolution, or I'll perform cross correlation or autocorrelation. In fact, autocorrelation case, correlation case is shown wrong here. In this case, this square pulse should be triangular pulse. So the rest of the thing is okay, the below, but this the wrong thing is here. This should be triangle. This is the only thing wrong here in this slide. So what I do in the AI is I find these projections or similarities. Let's go through an example which I'm quite fond of showing. Here are different faces, and I want to learn a generic face. I want to reconstruct these faces with as less information as possible. I have a large data set of faces. In this case, the data set is say 20 facial expressions with of 10 movement. and multiple pictures. So there's a large data set, and this is the dimensionality of the data set. If I see in the regular domain, the pixelated domain, this is the dimensionality of each picture which I want to learn. If I want try to learn this thing, this is very difficult, impossible. I want to summarize this information is as less basis components or eigenvalues and eigenvectors as much possible. So what I do is, from this data set, instead of going pixel by pixel, which has a dimension of 256 cross 256, what I do is I create certain handcrafted features. This first feature is easy to explain, so I'll explain. This first feature is just the mean of all the images, the baseline. The rest are differences. Rest are created by the differences of all the images. Some differences, some other transform which are there, and I create these are the basis vectors in my case, and I call these basis vectors eigenvectors as eigenfaces because I'm dealing with the faces. So if I want to reconstruct this face, this particular face, if I add the basis vector with the weight of 18.5 and this second basis vector, I get this picture. I increase the basis, I get a better picture. I increase the basis with more weights, I get even better representation. See, representation is improving, and I get more basis vectors, and now the reconstruction is almost same as this one. All these faces are the eigenfaces of the basis vectors, and these are the weights. Normally, these weights in AI, they are learned through some data-driven procedure. I mean, I will not go into that detail how it is done, but these weights are learned. But that's how a Hilbert space helps us to construct the images, say in this case. And this can be done then for every kind of a task. Let's see. This is one kind of a, learned filter that I showed you before also, that provides a similarity. What I do is I either craft these filters or I learn these filters from the data itself. And what these filters do is, these convolution filters basically find the similarity across the entire image. This filter applies scales across the entire image and finds the similarity, and then creates filter output, right? And then that filter output goes to the output volume and so on. I mean, this is the function that is happening here. Simple multiplication, component by component multiplication, and then summing it up. And this is what we call kernel in machine learning. Remember, I showed you the kernel at the very first slide of the Hilbert space. This is that similarity that is happening. Normally, these kernel are learned. Either we have to craft them, we have to create them. In old image processing, we used to create them. Nowadays, machine learning learns them on their own. But in general, with a lot of data and with a lot of filters, it becomes a computationally intractable job. And that is where quantum advantage comes in. Exactly how, I'll not explain, but generally you have seen, because the two things happen in the Hilbert space, so it is possible. If I can somehow map that one Hilbert space to another Hilbert space, the thing becomes easy, right? This is what exactly we do in the quantum machine learning.
Sorry to interrupt you, but there is a misunderstanding. My session is supposed to start at 3:30. So if you can wind up.
It's just wind up. So this is filter that is happening. And this is just creating this convolution filter is basically just creating the edge map. This edge map basically, then if you see here, the face is being detected in this using these various filters. This face is being detected, and these are the higher order filters that you can see. These are the higher order filters. These are the lower order filters, and then these are the higher order filters. And finally, this image is getting filtered and creating these higher order features. And finally, if you want to use this for the classification task, you see how these filters, higher order filters in the machine learning, basically create finally at the final layer with the weighted output. This feature set, this last layer feature set with the weighted output gives you the right classification with some weight or probability. Actually, this is not probability, but I mean we can calibrate it to have the probabilities. Again, coming back to the same slide, we want to learn this probability, so best option is quantum. And where we started. So this was all from my side. Any question? Otherwise, my session is closed. Inshallah, we'll meet tomorrow. No question? Thank you very much. Stick with us.
All right, maybe you guys should have a break of 5 minutes or 10 minutes before we start, right? And I see some laptops, that's exciting. So today we're gonna start the simulations together, right? And I also have a detailed session tomorrow. So today I don't know how many of you guys have joined Discord group, but there I've posted the how to initialize the setup and also the first demo. So I'm going to explain the first demo again today. We have 30 minutes short time, but I'm going to send this 2 demos to the group so you can compile it yourself later, right?
I didn't get the link.
You didn't get the link? Okay, then I'm not sure how many of you got the link, but I'm going to share this today so you can join right now and then I can share the sessions there, okay?
Share it through email or something.
I think with the email, do we have a group? For the people. Okay, then what we can do is basically I'm going to show the link here on the screen and you can type the link and can join it. Okay, so we're going to start with the 5 to 10 minutes of break, right? All right. Okay, can you guys hear me? I got this compliment yesterday that I speak way too much fast. So I'm gonna try to be slow this time. And I'm gonna repeat that what we did yesterday and what we're supposed to do today. And then tomorrow we can do it again. So first thing, yesterday I explained in a bit that we can import some libraries in quantum domain. And through these libraries, we can make quantum circuits and then we can simulate these circuits on quantum simulators, right? So it's not exactly the quantum computer we're working on, it's the quantum simulator we're dealing with because quantum hardware is a little bit difficult to make right now, or we cannot use it yet. It's not for the general purpose use, but we have to work with quantum simulators and it's more or less very accurate to quantum computers. I can say it, I don't know, but it gives you accuracy and you can work on it. And many companies around the world, they're working on the quantum simulators and then they're embedding their programs on quantum hardware, right? So yesterday I showed you that how can we create a quantum circuit with 1 qubit, and then how can we apply a poly X or poly Y gate on that qubit? Then we have to convert that circuit to an executable form and then simulate it, and then we get that what is the probability of that outcome. Today, the layout of my presentation is also a little simple, where I'm going to show you that we are importing some libraries, and then we are applying some gates, and also see the superposition and entanglements. But I would repeat this session tomorrow as well, because Dr. Madiha would be giving a session, and she's going to explain all these things that we have a session planned for teleportation and superdense coding tomorrow, right? So first thing, I'm going to start with the coding and I'm going to explain every block a little bit and then send you this code and the yesterday code on the group so you can simulate yourselves. I hope by now I shared a video that you can install a setup which use Python as a programming language. Then we have Anaconda that has pre-installed Python and Jupyter Notebook as an interactive coding session, right? So first, we have some libraries that we're importing. First, we are importing quantum circuits, quantum registers, which I explained yesterday, classical registers, and transpile. Transpile is a class that we can import from Qiskit that converts your circuit into executable format that can be used for quantum simulators or quantum computers, right? We have to do it. It's a predefined in the Qiskit that you have to use a function to convert into a suitable format, right? So you have formats for pictures and everything. So this is something that we have to do. Then we're importing a state vector class where we are saving our results. And then here is a simulator that we have to tell our computer that you have to use this execution machine for the circuits. And then for visualization, we have block vectors and histogram. And then here in the last two lines, you can see that we are working with the two kind of simulators. So we have air simulator and chasm simulator. I'm going to explain the difference between these two. So the air simulator, its purpose is to show you the quantum bit before measurement, right? And chasm simulator is basically resembles with the quantum hardware. So it shows you your output after measurement, right? So now what does it mean? You have a state 0 plus 1 divided by under root 2. And if you see the state, now it's not collapsed, right? We have probability of 0 half and probability of 1 half, right? But if we measure this state and we define a measurement operator as 0 or 1, then you would see that we would have only one state with a half probability. So these two states can be simulated with the two different simulators. We have chasm simulator that works with the measurement operators when your state is collapsed and you have no information about the exact quantum state before measurement. And the air simulator is basically when you have the exact information of the quantum state. Moving on, so these are the little demos that I made for the people who are just starting the Qiskit and they want to learn how can we do manipulation in the Qiskit. So for first thing, we are calling that NumPy. It's a library that we use for the graphs and plots and everything in Python. So we are explaining 0 as 1 0 vector. That would be 1 0 and then 1 as 0 1. So yesterday we was just writing a 0 qubit as 0, but today we want to have matrix multiplication in our Qiskit because that's easy and that's what we use. After that, what I'm doing is basically I am also giving our computer the matrix state of NOT gate. That is 0 1 1 0. So here I have defined my NOT gate, and then I am trying to calculate the dot product of NOT gate and 0. So it's basically a matrix multiplication that we're applying the NOT gate on the 0 qubit or on the 1 qubit the same way we were doing yesterday. But the thing is that now we're doing in the matrix subspace. Yesterday we were doing with the states, right? So it's however you want to, but as your data grows, the matrix multiplication is easy and you can use it, right? So what happens if you apply X on the 0 state, you get 0 1. So 0 1 was the 1 state. So it's working just fine. If you're applying 0 gate, NOT gate to 0, you have 1, and to 1, then you have a 0, right? This is a short circuit that I created a demo to see that if we want to use a Kazan simulator, then what happens? So in the first two lines, I am explaining two registers. Now, when you do work in the programming, if you guys have interest, yesterday I was explaining the quantum circuit bracket 1. I'm creating 1 qubit. But if you do the programming professionally, what you can do is basically you create registers first, and then you can manipulate the registers later on. So first I would create two registers, a classical register and a quantum register. And then I would say that for the ground circuit that I'm just measuring it. So what is happening that I am measuring qubit and putting that result into classical bit. So we are not applying any kind of manipulation or function over this no polyx gate. We're just measuring it. So I told you yesterday that it's a predefined gate that we would start with a zero state. If we don't explain the initial state, we have a zero state. If no work is done on the zero state, then we have zero with a probability 100%, right? And if we do a NOT gate over that qubit that we defined, then we would get one with a 100% probability, right? So for my own fascination, and I was curious, I always use this draw function to see what my circuit looks like. So it's like for the excited state, I'm applying NOT gate, and then I'm applying a measurement operator. This measurement operator is very important, right? Because if you have a state 0 plus 1, if you apply a measurement operator, this would collapse the state, right? So after collapsing, you see some of the state with some counts or some probability. So next, I told you yesterday, and I'm going to explain this a bit more, that we have to use quantum simulator with a predefined set of functions, right? For the programming, if we have to call some engine from IBM, then we have to go with certain rules. So the rules here is that we have to give circuits to transpile, to convert into executable format, and then run it, and then get the result. This is the way we get the results. And now we want to plot this result on the histogram. So when I say count, it means that you are getting a measurement outcome that how many of this is zero, how many times one occur. This counts, this simulator works after measurement. You should have this in mind before working on this. So I told you for the ground circuit state, we are not applying any operation, so we would get zero with the 100 probability. And if we do with excited state, then we get one with the 100 probability. Right. Now I'm going to go with this superposition circuit, and we would see that what happens with the superposition and how can we see the results or simulate this short circuits if we want to start with the Q-skit, right? Again, in the same way, I'm making our variable QC superposition, and then I'm applying a quantum circuit and I'm getting quantum resistors. It's a good way of programming. Good example that you make resistors first, then you can work and manipulate with the qubits after that, right? So the next I have to apply a Hadamard gate on our qubit. We would apply Hadamard gate on our qubit, and then next we have to measure the state, what the state looks like. So we would save this result on this classical resistor. And for my own curiosity, I have drawn this circuit, right? So I have Hadamard gate and measurement operator, and then the wire connecting is saying that we are measuring this operator on the classical resistor. Okay. Now I want to see the superposition states on the histogram, that are we creating a superposition in reality or not? This is the best example. So what would we do? We would pass this circuit to transpile. The transpile would convert this circuit into executable format. And then I would tell that you have to do it for 1025 times, right? Shorts is something that how many times your circuit is running, for it's 1 time or 2 times. So the maximum you can go is 1024 times, right? And then I want to see our result on the histogram. So this is the command that plots the result on the histogram. And what you would get is equal to, you would get 0 with a half probability and 1 with a half probability. But right now, this is not exact half probability because our quantum simulators are noisy. And every time this probability would change. But you have a relative half and half probability for this. All right, this is the Hadamard gate that I have applied. Now I want to see that if I apply 2 Hadamard gates, I have a qubit, I apply a Hadamard gate, I have a barrier, and then I apply again a Hadamard gate. So we all know as before this session that if you work with the quantum gates, those are reversible. Reversible means you can go back to the initial state after passing the state with the circuit. So if you apply the 2 Hadamard gate, you would get back to the initial state. So we started with the 0. We applied Hadamard gate to that, we get a superposition. And if we apply again the Hadamard gate, we would get the 0 back, right? So I want to check it. So for that, I saw that after this, I got 0 with 100 probability, right? So you always have to simulate your circuit if you want to see the results. That's very important. Okay. Now, next, what is happening that I want to see the state overlap, right? I want to do this whole calculation in matrix domain. Okay, now we know if we have to get the inner product or quantum inner product, that we have to use the conjugate and transpose, because we have complex numbers. So matrix would be converted into transpose and conjugate, and then this shows that you can get the same exact result if you do the dot product. Now here you can see half and half exact, but this is matrix multiplication. We're not simulating it over the quantum simulators. It's just matrix multiplication, and it would give you half and half. But when we simulate on the quantum simulators, you would always get this kind of counts, never always equal, because it's a noisy computer, noisy simulators, and you have to work on it. All right. I would finish this session and we would go tomorrow, because I think that I have to repeat this session tomorrow. Most of the audience lost because of the time confusion. I don't have the modified program, but I'm going to repeat this all again and we can do this again, right? So the last thing that I would explain a little bit in a short time would be the Bell state, which is entangled state, and how can we create it, okay? So I will just explain this and share this program with you. So tomorrow we can do it together. So first I'm getting quantum circuit with the 2 qubits and 2 classical bits. So now we have 2 qubits. Our states would start with the 0, 0, right? 2 qubits. Now what I'm doing is basically in the second program, I'm applying a Hadamard gate on the 0 qubit, right? So first qubit is converted into superposition while the second qubit remains the same. Now we have 0 plus 1 and we have a 0, right? This would get 0, 0. This would get 1, 0. And we have a state like 0, 0, 1, 0 divided by under root 2. The next part is doing control NOT gate. It's using first qubit as a control bit and the second qubit as a target bit. For 0, 0, it would remain the same. For 1, 0, it would convert the second bit into 1, 1. And what would we see? We have to see that if we compile or simulate this circuit, we should get 0, 0 and 1, 1 with the equal probability, right? Because the Bell state is entangled state. Now, this is the circuit. And after doing the simulation and calling our air simulator, because we want to see the quantum state, not after measurement state, which is called post measurement state, we would see that we have 0, 0 and 1, 1, right? Okay, since we have less audience, I have to repeat this tomorrow. So I would like to give you all a heads up that you should definitely join the Discord group. So I would be posting these 2 demos there, and tomorrow we will be simulating together, right? All right.
Thank you, ma'am. Thank you.
मेरे पास व्हाट्सएप का ग्रुप अभी है नहीं, लेकिन अगर कोई बना रहा है व्हाट्सएप का ग्रुप, डिस्कॉर्ड के ऊपर है, लेकिन अगर व्हाट्सएप पे कोई बना रहा है, क्योंकि डिस्कॉर्ड काफी लोगों ने ज्वाइन नहीं किया हुआ, ठीक है, मैं ये दो डेमोस पोस्ट कर दूंगी, लेकिन व्हाट्सएप का किसी ग्रुप है तो मेरे साथ शेयर कर लें। सर फरहान का भी किसी का कॉन्टेक्ट है तो मेरा नंबर ले लें, नहीं तो डिस्कॉर्ड का जो लिंक है ना, आप इसे ज्वाइन करेंगे तो आप डायरेक्ट ग्रुप पे लैंड करेंगे। उधर एक चैनल बना हुआ डेमो, उससे मैं सारी अपनी डेमोस डाल। परफेक्ट।
ये जो है ना ये वाला एक्सरा है ये रिलेटेड है ये और काफी Congratulations for your PhD.
Thank you very much. So now I'm looking for the postdoc next month. I'm going to have my convocation on 20th of June. So I just now I had one interview at Brain Indonesia. It's the national science and technology agency in and the next one time next week on the
You should also try to use it.
I was looking for the convocation, so
It's a job. Well, I mostly jobs. So, PhD, you can